we go. Let's see that. Not so hard. And I want to highlight the work of my team, the garden team, especially on the mission, the work of Celia Mulcahy, who plays with graduate students, Jane Morrison, Eddie Bergeron, my friend. So the nearest microshutter array on James Webb Space Telescope is a MOS, or a multi-object spectrograph. It allows you to observe hundreds to thousands of galaxies or objects simultaneously. Here it is in the laboratory. That's 4 quadrants of these little addressable shutters that you can open and close to create slits, or as we call it, slitlets, on top of your objects. Here are those 4 quadrants shown on the sky. The number to remember here is 3.5 arc minutes on a side. It's quite large. Here is a deep field filled with galaxies. We're going to zoom in on this box here, shown here. And the user here has defined open shutters on different areas of this of the image in order to get spectra from them. And then we zoom in here and you see the user has chosen to get spectra of this region and this region here. You don't get a spectrum in every pixel like you do for an IFU. This isn't what you get in IFU. You get in each spectrum the observer will get, in each pixel the observer gets a spectrum. Now IFUs are smaller. This IFU on this with the same wavelength on James Webb is 3 arc seconds on its side, as opposed to 3.5 arc minutes. So you can generally fit one of those high-redshift galaxies in here. So what do? We do something called slitless stacking to get a kind of marriage of both of them. We simply move the telescope move the telescope pointing across the faces of the galaxies. Brian Fleming mentioned he did his thesis like doing this on Tuesday. There are many other people who have done similar things from the space. So it's a little more complex than that. For larger objects, we do many steps. Here we have a large object with 6 steps. With smaller objects, we do less steps. 5 steps, 4, 3, 2. To the limit, we have 1 step with a single object. Luckily, in my field, in astronomy, smaller objects are fainter. So you're basically distributing the exposure time accordingly so that you're observing fainter objects with more time. And you can observe many objects at once. Now, we also do dithers over those bars so that we can get a more continuous map. So here's an observation with just doing the steps. Here we do kind of a snake dither pattern thread, as you would from the ground. So we did this with something called the garden survey on James Webb. I'm sorry, with our James Webb time called the garden survey. We used the microshutter as a multi-cataract view in this matter to observe 56 galaxies between redshifts 1 and 6. We used the high spectral resolution, which is 3,000 for Webb, giving us a spectral range. We chose a spectral range of 1.6 to 3 microns, chosen by grading, of course. We went very deep, so 60 hours on the source, 10 hours per step. I think I've had discussions about detectors with some of you in the room. We've been doing a lot of work on the reductions, obviously, to push into deeper. And then if we were to do this, I think we would have taken, an inordinate amount of time as opposed to just only like a 3-day project, including overhead. So what we do, we have now these 6 steps and 5 dithers, so 30 2D spectra per galaxy. We take them and we use the WCS and the JST data models, and we map that to the sky. So taking into account all the distortions in RA and DEC, and then we essentially drizzle it together to create a data cube. This work is led by the genius that is Jane Morrison. This is our sample at redshift 1, 2, 3 to 4, and then 5 to 6 down here. We went for bright galaxies because this was a cycle 1 pilot, and just interesting objects. Because this is a demonstration of technique here, I'm going to show you all of our data here. This is an earlier reduction. This made RGB images of the cubes by dividing image wavelength and setting the RGB values accordingly, taking pictures. I'm just walking through one of the steps. Okay, so this is the coffee pot galaxy. This is kind of easy. One object. We thought this was a fun merger, and we're going to write it up. So my student, Ezra Suke, is leading this with a lot of work done also by Celia Mulcahy. This is a Hubble and James Webb image. You can see it's a hot mess of the galaxy. There's a lot going on here. It's not just a spiral disk. We call it the coffee pot because that's what it looks like to us, and we're tired of memorizing galaxy numbers. Mm-hmm. So this is from an older reduction. We actually have a new reduction this week, so it gets even better. But this is an HWO line map from that data cube. What you see here, it's a little weird. You start seeing kind of spiral structure. Maybe an arm, maybe a bar here, and then another arm. I didn't expect to see anything like that. And we can also, from those emission lines, from that H-alpha line, look at how it changes in wavelength, which tells you how the galaxy the motions of the gas in that galaxy. So here we see the ring moving toward us, the red moving away from us. We see an overall sense of rotation. And Webb gives us this beautiful spatial resolution. We're starting to see all this kind of modelness in it. We start seeing this little red here. The other stuff is very good. Big field of study at these redshifts just don't show up in this map. I thought maybe the galaxy would be blowing itself up. It's this merger, it's highly star-forming. It's not. Here's the gas velocity dispersion map, and I find this incredibly beautiful. Again, we have better production as with this week even. But what we do is, you notice these star-forming clumps, they show up where it's black here. Where it's black here is low velocity dispersion. And these star-forming clumps forming in areas of low velocity dispersion, areas of low tumor Q. It's quite interesting. A lot of models you see these movies, they blow themselves up all the time. We're not seeing that here. We're seeing high velocity dispersion up to 180 kilometers per second, which is insane. Inter-arm region here, kind of in the center. And then this area here, inside the spiral arm. This is, and then we have these other kind of filamentary structures that are beautifully traced by this data. We call it cinnamon bun structure because we've been seeing it in some other galaxies. We've yet to understand what is going on. Very high values generally in the inter-arm regions. For those aficionados, there is yes, another arm out here, and one up here. We went deeper. We don't find this at redshift 0. This is very much at high redshift a phenomenon, and the first time we were able to see it is with Webb when we have this resolution. So, it's really starting to get me thinking this is a proto idea. In the local universe, we talk about disk galaxies, we talk about mergers, we have conferences on them separately almost. At higher redshift, you start having a lot more gas in these galaxies. We know that from other observations. When you start merging them together, you can then start forming disks, and there's been theoretical work on that showing that gas mergers count on disks. So some kind of disk or merger dichotomy might not even be what we should be approaching galaxies at redshift 2. So that was really kind of changing, at least my thought about how to really interpret galaxies at these redshifts. So in conclusion, silly stepping with JWST enabled multiplex IMU observations of multiple galaxies. It works, even with a small team, like we can do. Kinematic maps of the coffee pot showed it's not just a bunch of active clumps blowing winds out. The clumps actually form in regions of low velocity dispersion. And this map reveals these high gas velocity dispersion in the inter-arm regions that's really presenting a challenge to disk inversion models. So thank you.
So thank you very much, Susan. We will get hopefully a second microphone later. So I apologize, especially to the people online, which will not hear the Q&A. Hopefully this will be fixed. But let's start with questions.
Thanks for your presentation. Do you have classification if this could be an active galaxy, for example? Yeah.
So we looked at a lot of things, and down in here, I personally think it is. There's a lot of reasons why it's not in terms of things, but I think there's even a little jet here when you look at the,
Yeah, could be an AGN with outflows, for
I think
example, or sometimes we also see inflows, but I think that the loss dispersion is more indicative of outflows.
You can talk, I'm
Yeah.
here, we can figure that stuff.
Yeah.
First, Kevin.
Kevin Trans, University of Colorado. Thank you. Wonderful talk. Quick question about why it's so much faster than the IFU. Is it a sensitivity issue or is it mapping large fields of view? Why do you get such gigantic increases in the?
It is a sensitivity issue too. It is more sensitive than the IFU. We have other aspects that you want to worry about, like the bar shadow effect. So that's because in a given shutter, the throughput is not uniform. In fact, varies with radius from the center. So that's one of my significant areas of that bar shadow effect. But it's really a multiplex advantage. I mean, it's 3 days versus almost over 4 months.
I'm sorry, I guess that's what I'm asking. Why is the time difference so great?
Multiplex, because, I'm sorry, I'm using lingo. We can observe many galaxies at once in one amphitheater field of view.
Oh, in the same field.
And that's
Okay.
in Moss terminology, we call it multiplex, so sorry.
Okay, thanks.
Susan, when you scan the telescope, you keep your slit fixed on the instrument, but which gives you a certain type of internal calibration. Everything is consistent. But if you insist on the same point of the sky, scanning the telescope, you keep changing your aperture as it walks across, right?
I'm moving the telescope for this one.
Yes, that's the, but the galaxy at the bottom stays there, which means that each time you are changing the slit.
Configuring. I move, I reconfigure.
Right.
This one, I move off, I close this one, I reopen this one.
Exactly. So I was asking, there is any quality difference in the two strategies? Because you could move the slit pattern or you can move the telescope.
Oh.
What gives you better signal to noise?
No, you gotta worry about is broken shutters. With this technique, you can dance around the broken shutters. You have a broken column, a broken shutter randomly there. And then also, yeah, I think you're able to work around the broken shutters. And then also with this, you're just giving it more exposure time. Here, so the baristas, Shadal and Tucker Jones did a program where they kind of ran it like a typewriter. And you can do that too, but you're stuck with the broken shutters and then with not optimally giving things beautiful exposure time. It's a lot less than you can plan. For us, we were, with APT, we had to do a lot of work. Yeah.
Just one more, if it is it a quick question? Maybe not. Go for it, Vivian.
Okay, yeah, beautiful work. I love the demonstration of technique. In terms of science, do you have enough line diagnostics to look at shocks? Because actually, in one of our papers recently, thank you. One of our papers recently, without an HN, we looked at Cerberus galaxy, and we actually do see an anti-correlation between like star cluster densities and like shock fraction, and that actually shocked us and intended. I was wondering whether or not you have the shock diagnostic lines.
So first of all, I think it shocks too. I agree, we'll talk. I think in this galaxy, we might not be regions of the spectrum land in between the detectors. I think this one we got a little unlucky. With others we do. At least we have like a silicon line. That's right. Silver or something. I forgot. Yeah, we'll talk. So yeah, I think the shafts were perfect.
There were a few other questions, but please post them on the Slack. So let's thank Susan again. Do you want to ask your questions?
I encourage you to say your name before you ask your questions, and I've been enrolled myself and reintroduce myself. I'm Annalisa De Chia. So the next speaker is Joe Borgia, and he will talk about New Mexico State University. We'll talk about mapping and active waves and thermal instabilities in the circumgalactic medium.
Should be up. still don't see you online.
Thanks everyone for already so far. I'm delighted to be presenting this science case to map the CCP HWO. This is one of 3 science cases to emerge from the EIGM-CGM working group that I co-led with Sanj Portekar, who's giving the talk right after me. I also want to highlight our other science case led by Megan Tillman, who's presenting that in a poster downstairs, and I believe will be on the job market this fall. Thanks so much to everyone who helped out with this, the technology and instrument experts who engaged with us and allowed us to root our dreams in some semblance of reality. Left to my own devices, I clearly am not very rooted in reality, so thanks to Steve and Kevin and BT and everyone. Moving on here. CGM, we've heard about its importance to galaxy formation and evolution all week at a few points during the week. And so this figure on the right highlights 2 key aspects of the CGM. One is its multi-scale nature, with larger scales such as tens to hundreds of kiloparsecs.
Oh, yeah, this one's.
Okay, so 2 key scales of the CGM. One is the larger scale phenomena, such as galactic winds, outflows, inflows, on scales of tens to hundreds of kiloparsecs. And then on smaller scales, we have the microphysics of what's happening in the CGM, thanks to thermal instabilities and radiative mixing boundary layers. These tend to happen on scales of 1 to sort of 10 parsecs. The CGM is also multi-phase, as denoted by the color scheme here. Bluer colors correspond to cooler gas at 10 to the 4 Kelvin, yellow and orange 10 to the 5, 10 to the 6, and beyond. So these are the key regimes that are to which we're sensitive in the ultraviolet. So HWO will take the first picture of the CGM. So this is the spectacular Makani object. Mapped from the ground. There's been other work done from myself, Nikki Nielsen, Serena Perrota, etc., all showing through either optical emission lines or near UV lines that are redshifted into the optical envelopes of gas that span dozens of kiloparsecs from the central galaxy regions. So this work is inherently limited from the ground. The optical line tracers are simply not as strong as the far UV counterparts that can trace these phases of gas. Furthermore, when we can use near UV tracers like magnesium-2, we have to redshift the galaxy into the optical, and we sacrifice quite a bit in spatial resolution from the ground. So this is really an ultraviolet game in the long run. And in the ultraviolet, we have some amazing diagnostics of the diffuse multi-phase gas. This phase space diagram here in temperature and density highlights several regions where different spectral tracers trace regions of temperature and density. So I'll highlight the oxygen 6 doublet here, tracing gas of 10 to the 5.5 Kelvin. Not shown, which we'll also focus on, is H1 Lyman alpha, which will mostly trace the cooler 10 to the 4 Kelvin gas. You see the rest frame wavelengths here. Oxygen 6, for example, at 1032, 1037, and redshift 0 is basically inaccessible with HST. Wavelengths below 1150 angstroms are basically inaccessible at the current time. And this is going to radically change with HWO. So the object here, thinking about the large scale structure of the CGM, so returning to Makani, mapped here in oxygen 2 emission, showing a biconical outflow spanning 100 kiloparsecs from tip to tip. So if we were to map this with a single shot with a multi-object spectrograph on HWO, we can use this scale as a guide. So these are physical distances subtended by various angular scales. as a function of the redshift. So at redshift of about 0.01, we could map this 100 kiloparsec region with an 8 arc-minute field of view MOS instrument. Thinking about spatial resolution, possible spatial resolutions are shown with the dashed lines. At half an arc second resolution, that resolves 100 parsec scales. So a really incredible view of the CGM. So we wanted to do some mock observations, given some sort of current working instrumental parameters for HWO. So we selected a Milky Way type galaxy from the TNG 50 simulation that's shown how it might look in starlight in the image to the right. We put it at redshift 0.01, assume an 8-meter HWO, and observe for 100 kiloseconds. So what we see, this is both Lyman alpha emission and Lyman alpha emission and oxygen 6 emission predictions from TNG 50. Surface brightness is shown there, just focusing on the Lyman alpha emission. Here, you see surface brightnesses of 10 to the minus 18, all the way up to 10 to the minus 15, across sort of scales of 300 kiloparsecs. That's all well and good. If we put our 10 arc-minute field of view MOS toward the central regions of this, run it through some exposure time calculations for 100 kiloseconds, the signal to noise ratio we get over this entire map essentially exceeds 100. So this is a log scale, just an incredible booming signal from Lyman alpha as predicted by these simulations that we could easily map with HWO. Oxygen 6 now a bit fainter, 10 to the minus 19, 10 to the minus 17, its brightest points in surface brightness. Still, in 100 kiloseconds, the same observation that we simulated for Lyman alpha, the same shot, we basically get oxygen 6 with signal to noise exceeding 10 virtually across this entire field of view. So simply a groundbreaking, unprecedented view of the circumgalactic medium. And this may even be a pessimistic view of what we would see in oxygen 6 from HWO. Makani was recently mapped in oxygen 6 using a pseudo narrowband technique by Ha et al. That map is shown here. Looking at this surface brightness scale, we see surface brightness is exceeding 10 to the minus 16 ergs per second per centimeter squared per arc second squared. And if I just to try to make an apples to apples comparison, the surface brightness from that same TNG 50 galaxy here, next to it, you see far fainter predictions from the emission, far lesser extent of that CGM. And I'll add, narrowband imaging gives you no velocity information. So HWO would not only give you the spectral information, the kinematics of this gas, but we could do this for a statistical sample of galaxies, right? Not just one special object at a sweet spot in redshift. Okay. So I'd like to turn now to the small scale structure of the CGM. This schematic from the seminal paper by McCord et al. Shows a cooling gas cloud in the CGM going from the sort of hot halo conditions at 10 to the 6 Kelvin down through 10 to the 4 Kelvin, at which point it may fragment and shatter into these smaller cloudlets that are denser with lower volume filling factor. So these predictions are born out of simulations as well. So I just show one example from the Gibble project, the Foggy project. Other simulations have shown similar results. When you crank up the resolution in your hydro, you reveal smaller and smaller substructure. The smallest substructures shown here are about 30 parsecs. So we wanted to inform our HWO planned observations based on this small scale structure. So this is just to show the temperature and density dependence of cloud size under this shattering regime. The contours show the cloud sizes. So just changing the orientation here, we can highlight different regimes of cloud cooling as a function of the gas density and predict the cloud size those would produce. So for a relevant range of CGM density, 10 to the minus 4, 10 to the minus 2 per centimeter cubed, we set our spatial resolution goal for now an integral field unit observation at 10 parsecs, which would allow us to observe clouds in the shadowing regime and rule out those larger cloud scenarios. So coming back to our scale once more, for a 10 arcsecond field of view IFU, this would allow us to map 3 kiloparsecs of that substructure. I realize this is an ambitious field of view for the IFU. We could live with a little smaller than that, but an appreciable region of the larger mapped with the MOS and 50 milliarcsecond resolution would get us down to this 10 parsecs at redshift 0.01. So I'm done there just to summarize. This will not only be transformative for CGM science, but I believe will be marquee astrophysics for the Habitable Worlds Observatory. We can do it. The leadership, project leadership is enthusiastic. And behind this, the technology experts, the instrument builders are paving the way, enabling this. And I think we as observers and scientists and theorists, it's really on us to continue this momentum to try to face into the challenges that we're going to have when we are delivered this beautiful data. So thank you so much. I'll take any questions. Here's our big table. Thank you.
Joe? Online?
I have a question. Which is the wavelength?
You have the microphone.
Oh, okay, if I can, I'm sorry. Which is the wavelength, the massive wavelength of this? This is your proposal to use the IFU, the UV IFU?
This is both the MOS and the IFU.
Both MOS and IFU, yeah. So you are proposing to go until that of wavelength range?
So the wavelength range of importance for us is, I did this in 2 discrete regions
Okay.
because we have a set of diagnostics.
Okay,
in the-
so it's more in the UV, yeah.
Oh, yeah.
Yeah.
Oh, yeah, this is UV science, 100%.
Thank you.
Any more questions in the audience? I have a small question for you. Like, what are the prospects with the habitable worlds to see differences in chemical compositions between inflowing gas and outflowing gas?
Yeah, so all that's fair game. The question was about chemical composition. I just highlighted on basically structure and morphology of the CGM, but no, those chemical tracers are essentially covered simultaneously that I showed in the previous slide. When you have carbon 3, you have silicon 2, 3, and 4. You have carbon 4, carbon 2, all of these various ions that are basically all in play, all in a single shot, given this wavelength coverage.
Fantastic, thank you. So let's thank again, Joe. Our next speaker is Sanch from Arizona State University. And she will talk about characterizing gas flows through observations of the disk CGM interface with Habitable Worlds Observatory. And while we're waiting, I would like to thank Jessica Noviello and all the members of the LOC for all the great support they're giving and bringing us microphones and all the help.
Well, just one super quick announcement is that if you look above, you'll see little green lights. These are microphones, omnidirectional. They are live. So people online can hear rustling and side conversations and some comments about sometimes. So just be mindful, and I mean, I'm not asking you to be completely silent, but just be aware that sound is being picked up from everywhere in this room.
Good afternoon, everyone. I'm the other co-chair of the CGM ITM group. And today I'm going to talk about one of the second science case that we developed. And this is a little closer to the galaxy, and this is the disk halo interface. So the way I see it from the decadal recommendation of the cosmic ecosystem and the idea of tracing gas flow. It's very similar to the analogy for monitoring the gates. So in this case, you can be the gatekeeper to sort of understand who is coming into the room, who is coming out. So this is a way that will help us quantify that and allow us to connect to processes that some of you might be seeing inside the disk, like star formation, gas flows, etc. And that's kind of where we are needing more kinematics. So Joe had already sort of suggested that we could do all that. But I would focus a little bit more into the kinematics here. Not able to move the slides. So what we want to do is identify these gas flows directly. And this is a really good space because then we can really connect to where the gas is moving in the disk or the stars are moving and where the gas just outside the connection of the disk CGM is moving. And this is critical because we want to trace inflows, outflows, maybe things that are recycling, all of that. And that sort of connects to feedback processes, etc., that we are very interested in. Now, disk-scale interface is just a general term for this region. There are many processes or structures that exist in this region. So I'm going to just quickly go over some of them. So we have extended disks of galaxies. So that's the gas beyond the stellar disk. This is a very established phenomena in the nearby universe, 21 centimeter. I get to see it in many galaxies. But there are limitations. Just because it's 21 centimeter, you have these radio windows, you can't go that far, it's very expensive. And to really quantify how much gas is there, you really need a good census of it. So this brings me to the technique. So I'm going to mostly focus on absorption spectroscopy. And this is work done in 2010, fairly a long time back. And this is one of the ways we can show that how the galaxy is moving its kinematics based on H-alpha or oxygen 2, 3, whichever line you have access to, and then absorption from the quasar, which can actually show its gases moving along with the disk or not, and you can do this modeling to understand what's driving it. In addition to that, we also know there are these high velocity clouds, very well studied in the Milky Way. But we don't really know if all galaxies have these structures. And this is very interesting because our study of the Milky Way has suggested that about 1 solar mass per year, similar to the star formation rate of this Milky Way, is falling in the high velocity clouds. They can put two and two together. So broadly speaking, it's sort of a mix of maybe things that are recycling, things that are falling in, things that maybe just stabilizing the halo and not doing anything. But that's a very, very crucial aspect of how gas flows in and out of galaxies. And finally, we are very interested in feedback processes, but not all the feedback is that extreme that you can see in these very massive black hole driven feedback or star formation driven feedback. Most of the time, they're kind of mellow. For example, the Fermi bubble of the Milky Way, it's not that big, but it still has very much information about how the black hole in the Milky Way might be growing. And of course, we could have smaller feedback processes, loops, where gas comes in and out, but it doesn't go out of the CGM or even to the outer CGM. And this is critical because this is where we can connect to the disk and see its velocity and quantify it. So these are the different mechanisms, but I wanted to now focus on what do we need on habitable worlds to make this possible. So before I go in, this is not for reading. I just wanted to show you there are a whole lot of species that we have access to in the UV. And they give us various different information about different things. It could be either cold or molecular gas. It could be cooler transitions that are partially ionized, maybe warmer transitions, which are more or less ionized, and very hot ions, which are completely ionized, tracing different types of phenomena. And they tend to be at the same, very similar places with similar kinematics. So that's kind of where the problem lies. And one of the things that we will have access to if you go far in the UV is molecular hydrogen. So let me just start with the figure here. It's a figure that shows various different lines. And for extragalactic systems, we expect all these metal lines. But for galactic systems, when we look at dense things, and maybe even extragalactic system where we are looking very close to the disk, we can detect all these lines, including higher series hydrogen lines. That gives us a very good column density, which is a big problem in the UV. Sometimes CO lines, deuterium lines, very important for nuclear synthesis. And of course, molecular hydrogen line, which directly tells us how much molecular gas is there, not just co-molecular gas like the JWST or CO measurements that gives the indirect measurement, but we can directly measure the molecular hydrogen. So this gives us a set of parameters, and I'm going to give a quick touch upon quick requirements because I have limited time. So the first thing we want is sensitivity. That is basically the thing that's stopping us from doing this science with Hubble, other than the fact that Hubble doesn't go far in the blue side of the spectrum. For example, if we want to study this halo interface in other galaxies, depending on how you define it, is it 20 kbc or 30? At cost sensitivity, we have a dozen such sources, and also not the blue end of these. But if we go down to maybe 2 magnitudes further down, we will basically increase the sample by an order of magnitude or more. And that gives us statistics, that gives us the power to study different types of galaxies and different phenomena. In fact, at that point, we will have multiple quasars per galaxy, so where we don't have to worry about the type of galaxy that we are looking at. And here is a plot that shows different amounts of sources we will find. So it's basically the same plot at 20, 30, and 50 kbc from any galaxy. And this is of course statisticals, but you can see that you will have many more sources. These are the number of sources that will be available for spectroscopy, 1, and so on. And the magnitudes, as you go to fainter sources, you will find many more. Something that we expect, but this is more quantifying it. All right. Now, this is the part you might be thinking, 2 magnitudes is not that big a deal. We don't really need to make habitable worlds just for 2 magnitudes. But we need 2 magnitudes and very high resolution. So I apologize for the busy slide here, but all you have to focus is one of these. They're just repeats. So let's just start with this one. It's a sideline, synthetic sideline that goes through a L-star galaxy at 17-ish kiloparsec. The black is the data that you'll get with infinite resolution. The blue is the resolution that's shown in here. So it's basically the line spread function that spreads the data. But as you can see, maybe for very high ions, you might be okay. And those of you who use COST might connect the dots. 20,000 is the best you can get with COST. And as you move 20,000, the poorer ions, what you get and what it is basically no correlation. And you're missing all the structure over here. You get a little better at 33,000, maybe 50,000, you can actually see them. But to get the best resolution, you need 100,000. And I mentioned this because in the disk halo interface, you will see all these things happening. So individual clouds might have very different properties, very different metallicities, very different kinematics, internal structures, and tracing different processes. So you really need this kind of resolution and sensitivity to magnitudes below. The other thing I quickly want to mention, which is not a problem, is we do need a MOS that is big enough, which is about 6 by 6. Anything bigger is fine, but something like this galaxy NGC 3432, which this is a Hubble image of this part of the galaxy here, right here. And to do this galaxy, you actually have 3 quasars that will be accessible with habitable worlds. Right now, we have data on this with COST, but what we could do is if we have a MOS, we can place the slits over here on the quasars on the galaxy. There's a satellite galaxy here, some empty click on some of the CGM where we can detect integrated emissions, etc. So we need all of that. So that was kind of the requirement. More information is on here in the paper, but I want to stop here and essentially drill down that we really need very high resolution, 100,000, and we need as blue as possible, at least 1,000 angstrom, preferably 970 or 940. And 940, please don't be angry at me if I say 940, it's like, is she out of her mind? Because Fuse has already done that. It's just that probably we don't have that many sources bright enough to do that. Anyway, I'll stop here and take questions.
Thank you, Sans. I also endorse the 100,000 spectral resolution. So questions for online? Video?
Vivian, you can I was wondering, and it's a naive question, so because I only know the molecular hydrogen lines in the infrared and infrared, so what advantage do we have, do we gain from using the UV H2 lines?
Very good question. So in the UV, anything that's molecular hydrogen, hot or cold, will show up. So mostly in the infrared, you're looking at the cooler clumps, but in this halo interface, you could actually have molecular hydrogen, which is much warmer. And I don't know if it's proven beyond doubt, but majority of the molecular hydrogen in the disk halo interface is expected to be warm, 1,000 Kelvin or something like that. So that is clearly detectable with the UV lines.
Hi, Sanch. So in that image you just showed, you had 3 background quasars. Would you use the MOS for anything else besides those quasars?
So what we would like is, sorry, this doesn't go back. But so the MOS would allow us to get spectra of the galaxy, because ultimately we want to connect what's in the quasar, like what sightline, to the kinematics of the gas, so we can actually estimate if things are coming, outflows are there, and the stellar population. In addition, we can get redshift of nearby systems, which are generally faint, or just study the stellar population there. And also the empty space, which will, if you integrate enough of those, you can collect many slitlets, put them on these blank spaces and just integrate enough, or sort of stack them, you can get the emission. So it'll be kind of like a emission absorption together to get the densities, etc.
But you wouldn't need the 100,000 for those observations.
So yes, it's mostly for the quasar.
I bring it up because 100,000 starts to play with physics, like
Yeah.
possibilities
In a MOS mode.
in a MOS mode, but in a shell mode, for instance, no problem. So you could conceivably just hit those 3 quasars within a shell and then go back with the MOS and tile all the other things you want.
Yeah.
A little less efficient, but I hate to say it, but 100,000 in a normal grading mode
It might be difficult.
is I don't like using the word impossible, but it'd be fun.
Sporty.
Yeah.
Spicy.
All right. Very quick online question from Patricia Nezek. If you need R of 100,000, how much integration time will you need?
Yeah, that brings us to the size of the telescope, which of course there are many things that I'm not qualified to measure, qualified to say about it. But for something like a 28th or 21st magnitude quasar with 4 hours, we could get that resolution with the 8-meter class.
Yeah.
So yeah, so that might be a motivation to go for it.
Thank you, Sans. Let's thank Sans again. Our next speaker is Greco Oyarzun from Johns Hopkins University. They'll talk about constraining the baryon cycle with damped Lyman alpha absorbers and the UV integral field spectrograph at the Habitable Worlds Observatory.
we have like 20%.
Somebody's with us.
Yeah.
It's green now, we can start.
Right. Hello, everyone. My name is Grego Yasun, and I am a postdoc at Johns Hopkins. And I am a member of the Magnus Collaboration. In particular, I work with Mark Rafelsky, who himself is a space telescope. And I'm happy to be here to talk about how we have been using IFUs to constrain the baryon cycle at high redshifts. So I want to start with what brings us together here, which is trying to understand our cosmic origin. And when I think about our cosmic origins, I think about how the cosmic densities of different forms of baryonic matter evolve with redshift. So what we see here is how the cosmic densities of neutral gas in green, molecular gas in black, and stars in red evolve from redshift 6 to redshift 0. And this figure reminds us that early on in the universe, baryonic matter was dominated by a neutral hydrogen gas. And yet today, we find ourselves surrounded by immense amounts of complexity in the form of heavy elements, molecules, and light. And therefore, it becomes apparent that in order to understand how galaxies were responsible for this transformation, we need to understand neutral gas, we need to understand the properties of neutral gas, and how galaxies process that neutral gas in the context of the baryon cycle. So then we ask ourselves the question, how do we study neutral gas throughout the universe? And one primary way of doing that, especially at high redshift, is to use down-dimensional alpha absorbers, or DLAs for short. So what's a DLA? A DLA is a neutral hydrogen gas cloud that's detected in absorption, and it features a particularly high neutral gas column density. So what does all of that mean? So we take the spectrum of a background source, ionizing background source like a quasar, take a high resolution spectrum like what we see here, and sometimes you identify high equivalent with absorption features, such as the one with, that's highlighted with the red arrow, and that's a DLA. And here the key feature of the DLA is the high equivalent width of the absorption feature, which is indicative of the high column density that I was referring to. So why do we care about the column density? For two main reasons. One, it's the gas that we believe is associated with star formation in galaxies. And two, because of the high column density, it turns out that DLAs dominate neutral cosmic gas throughout the universe in terms of energy density. So what one can do is utilize the incidence rate of DLAs throughout the universe to constrain something, for example, like the cosmic density of neutral gas. We did that earlier this year as part of the QC5 survey that did exactly that, constrain the incidence rate of DLAs at redshift 5. And so this is what we see in this figure. Y-axis is for H1, for the cosmic density of neutral hydrogen gas. On the x-axis, we see redshift. This is the star that you see at redshift 5. This is what we recovered with this survey by constraining the incidence rate of down-dimensional absorbers. In this study, we also compiled measurements from DLAs at incidence rates at lower redshift and measurements from 21 centimeter emission. And what we concluded is that the cosmic density of neutral gas increases from redshift 5, peaks at about redshift 3, and drops towards redshift 0. So what this is telling you is that galaxies build up their gas with time. And the amount of gas in galaxies throughout the universe peaks at about redshift 3, shortly before cosmic noon. And then it starts to drop as star formation throughout the universe starts to decrease. So what I've talked about so far is basically illustrating how DLAs are extremely useful to understand cosmic neutral gas. But the reality is that we haven't been able to systematically connect DLAs with the population of galaxies detected in the mission. As an example, I'm showing here the number of associations between DLAs and galaxies established between 1990 and 2014. And you can see that despite the number of efforts, associations were established. And that began to change about 10 years ago. And that's mainly because of integral field spectrographs. So it is in this context of trying to connect DLAs with the galaxy population in the context of the baryon cycle that I want to introduce to you the CAG survey, which stands for KCWI Analysis of Gas Around Galaxies. So here KCWI is the integral field spectrograph at the Keck telescopes, and the goal is to spectroscopically connect Lyman alpha absorption with Lyman alpha emission. And I'm showing here what the data set of the CAG survey looks like for a single field. So this is a single quasar field that features 3 different DLAs at 3 different redshifts. So on the left, we see a DLA. So we see the integrated KCWI data cube at a redshift of 3.8, a redshift of 4.1, and a redshift of 4.8. And what we did was to start searching for Lyman alpha emission in this field that features 3 DLAs. For the lowest redshift DLA, the one on the left, we do not detect any significant Lyman alpha emission. For the intermediate redshift DLA, we detect a tentative Lyman alpha emitter. Sorry, yes, the location of the DLAs is right at the center of the field. For the intermediate redshift DLA at 4.1, redshift 4.1, we detect a tentative Lyman alpha emitter that you see is located near the edge of the field of view of KCWI, which corresponds to, at this redshift, to a projected physical separation or impact parameter of about 100 kiloparsecs. And then for the highest redshift DLA, we detect 4 distinct Lyman alpha emitting sources, for which you see the spectra here, and a wide variety of impact parameters. So this kind of illustrates what we're doing with this survey for a single quasar field. The CAG survey in totality targets as many as 17 quasar sightlines, where all of them were selected based on the high number of DLAs that they feature. So this is what you see here. Each line corresponds to a different quasar sightline, and the x-axis here is wavelength. And each bar here shows the location of the down Lyman alpha absorber in wavelength space. So we can construct a histogram of the redshifts of the DLAs in the survey, and you can see that they're mostly between redshift 3 and redshift 5. So I'm happy to share that we have taken all the data, we have reduced all the data, and we have detected 25 Lyman alpha emitters around our sample of 36 DLAs in total. You can see some of the initial lines in this figure. And very quickly share some preliminary results. What you're seeing here is on the x-axis is the metallicity of the neutral gas that's measured in absorption. Greater metallicity is to the right, lower metallicity to the left. And the y-axis is the impact parameter. So as I was saying, the projected physical separation between the galaxy detected emission and the gas, the neutral gas detected in absorption. And this is the compilation of results from the literature, and measurements from CAG here correspond to the black circles for significant detections and blue circles for tentative detections. What we see is an indication of an anticorrelation between impact parameter and DLA metallicity, which is basically consistent with expectations we would have that the closer the neutral gas is to galaxies, the more enriched that gas is going to be. And the second result that is preliminary because we're still working on our class calibration, but in the context of the literature, we're seeing a tentative trend that Lyman alpha luminosity of the galaxy increases with impact parameter, which is perhaps an indication that conditions around neutral gas are not conducive to Lyman alpha photon escape, perhaps due to, of course, the neutral gas itself and the abundance of dust. So for the last part of the talk, I want to touch on how the prospect of an IFU at HWO would take these types of analysis to the next level. So everything that I was talking about, we're of course limited to doing so at redshift of 2 or greater. But with HWO and a UV IFU, we will be able to do this at anything below redshift 2. And that, of course, has the benefit of being able to take advantage of a larger angular sizes of galaxies, which increases, of course, the spatial resolution that one can achieve, but also the availability of quasar cyclings. And here I have a wish list of what such an instrument would look like if I had the opportunity to choose the specs of that instrument. And I'm happy after these last few days of the conference that these don't seem out of reach with what has been discussed. We don't require absurd spectral resolutions. We don't just need to detect emission lines. But perhaps what the field of view is perhaps what's the most constraining. At the very least, we would like 10 by 10 arc seconds, but ideally would go higher than that. And I'll leave out my summary and take any questions. Thank you.
Thank you. Question for Marco? Do we have any questions on the line? Please go ahead.
What is the highest column density of a down planet alpha system that's ever been?
Thinking about 10 to the 22 or so.
Even up to 23 with gamma reversed.
Yeah.
Do you have a comment why the gas density goes increases from the most recent objects until, I don't know, I think it was cosmic moon, and that decreases? I cannot understand very well this, how you interpret this.
Right. Okay, so what you see here is this is what we understood what the neutral gas how the redshift was like before our survey. So we understood it to keep going up with the redshift, right? So the distinction here that one needs to make is that we're looking at the gas, the high column density gas for the most part, because we're looking at DLAs. So this is the gas associated with galaxies. So it stands to reason that the high column density gas in galaxies needs to accrete onto halos to assemble to manage to reach the high column densities that trigger star formation. So it's all about like what kind of gas are we talking about, and when we talk about the gas that is in galaxies that triggers star formation, then that does need to build up, and it makes sense that it peaks just before cosmic moon.
Thank you. We have one more question.
Yeah, thanks for that, Greco. On the 25 galaxies, 36 DLAs, so that's some of those DLAs have multiple galaxies, right? And what's the maximum impact parameter that you draw associations there?
Right, so it's not square. So we use the large field configuration, so it was like you can't see, but this is 20 arc seconds and 30. So in terms of impact parameters, so just half, right? Because you only get half from the position of the DLA. So this is like 120 kPc at redshift 4 or so, and here is just like 75. So it's like 150 times 250 or something like that.
Is that consistent with the associations drawn before? You shown like 10 by 2010 and then 30 between 2010 and 2025. Is that similar impact parameter ranges to draw those associations?
No, that's a good question. So because these were pre-IFUs, so all the ones on the left, they're just based on like searches that like very low impact parameters. So like putting a slit on the quasar and rotating the slit and see if you can see anything like very close to the quasar. And so the shift from before to now, big part of it is just like being able to identify galaxies that are not necessarily within 10 kPc of the DLA.
It must be to see this many detections of DLA galaxies. Congrats. Let's thank again Greco. Next speaker is Jorgen Escudé. from University of Barcelona, and we'll talk about super magnified stars in lensing clusters and small-scale structure in dark matter.
Thank you. Hear me okay? Okay now? Okay, what I want to talk about is about these super magnified stars that are seen in lensing clusters of galaxies. And the interest in this is that, well, there have been a few talks this morning about dark matter. Can HWO help figure out what the dark matter is? And I'm going to tell you one way in which HWO could be quite interesting for this. Through what's called these super magnified stars, that we got this here, in lensing clusters. And in particular, this can help us figure out, is there small scale structure in the dark matter on scales that are quite small, let's say parsec or less, for which at present we have no observations, no clues on whether dark matter is smooth or is it shows any clumpiness. So we have the past slides here, please. Okay, so
unfortunately, the clicker is not working, so we're doing that.
I see. Okay, thank you. Okay, so these super magnified stars are individual stars that can actually be seen. They have been discovered with Hubble Space Telescope and now with James Webb at redshift 1 or 2 or even a little higher. Because they are highly magnified by, say, a factor of 1,000, and then they become observable. Typically, they're the most luminous stars in a galaxy, like supergiants, and then they are seen in some of these arcs or lensed galaxies. This is the first such arc that was discovered in a lensing cluster. It's in ABL 370. Was discovered in 1987, but then when Hubble has taken images of it, then we can see much more in detail. So here's the galaxy, and then it gets stretched up here, and here you can see multiple images, double images of the same thing. You can actually look in detail and see that these are multiple images. So there's a critical line going through here, and then the bulge here, the right part gets multiplied several times. Here's the end of the galaxy, this spiral disk galaxy. And whenever we are in one of these regions where we see the double image of the parts of the galaxy splitting from a critical line, that's when you get very, very high magnification. And if there is a star sitting right in that place in the galaxy, you will then see it, you can see a single star. So it will reach maximum magnification when crossing the lensing caustic. So a galaxy can look something like this, and the idea is that because of the transverse motion, right, the caustic is sweeping through the galaxy, and then you just see the structures go through the caustic. Now, if the lens were smoothly distributed mass, then there will be just one caustic, but actually there's more because of the small scale irregularities in the mass may produce many microcaustics. There is a precise prediction of the light curve shape you should see when a point source of light crosses a caustic, which goes like that. This is for a uniform disk, and for the point source would be just 1 over the square root of the distance to the caustic, so therefore 1 over the square root of time when you look at this move through. This is not, however, what you see. If there were no microlensing, if there was a smooth mass distribution, then a star could be magnified as much as 1 million. That's basically the square root of the Einstein radius of the cluster divided by the angular size of your star. It can be as high as 1 million. But crossings would be very rare because you only get to see rather luminous stars when they cross the caustic. That wouldn't happen very often. Instead of this, what we have is that there is some small-scale structure, which we know is there. Even if the dark matter is perfectly smooth, we know that there must at least be intracluster stars, right? Now, on top of that arc, there is no galaxy, but we know that in clusters, there's intracluster stars because of all the tidal stripping going on at the outer parts of galaxies. So everywhere there's intracluster stars. This reduces the maximum magnification to 10 to the 3. This formula, the peak magnification, is basically this part, distance divided by radius of the star square root. But then, so it reduces that. Kappa star is the surface density in the intercluster stars, goes to sigma star to the -3/4. You can show that analytically, but then the point is you get many, many microcaustic crossings. And so the frequency of these things is much higher. So overall, the presence of these intercluster stars actually helps detect this phenomenon, because even though the maximum magnification is lower, you just get many more such crossings. So then there's variability of the light. This is a simulation showing what happens, that here is the overall caustic of the cluster, right? But then when you put the intercluster star, you just get many, many peaks. Okay, here they are less frequent, here they are more frequent. Actually, this is a simulation with far fewer intercluster stars than there are in reality. It's too difficult to do it realistically because of the large number of stars you need to simulate these microlensing calculations. But so that's the point, that just to illustrate what we expect to see, okay? Now the question then is there are a small scale structure in the lensing mass, in addition to the intercluster stars? These intercluster stars account for only perhaps 1% of the projected mass of the cluster. There, right? 10% is in the hot emitting, X-ray emitting gas, 90% is in the dark matter. But the question that we would like to ask is there small scale structure in most of the mass in the dark matter? We have to tell if there is something in addition to the intercluster stars. So one way to tell this would be, well, this is first of all the first such supermagnified star that was discovered, Kelly et al. In the cluster MAX J1149. That's part of the lensing cluster. Here there is an image of a background galaxy, a nice spiral galaxy here. Here there's another image of the same galaxy and another, so 3 images of the galaxy. And there is the outer part, a spiral arc in the outer part of this galaxy is going into the critical line over here, and you have 2 images of the spiral arcs over here, right? So here is where a lensing was discovered. We think this is a star belonging to this galaxy, and here it was buried, okay? So, that's some detailed observations of how this thing was buried. There was a lot of observations given at a specific time. A simulation showed what we would expect. We cannot reproduce that exactly, but just simulate statistically the typical thing you might expect. And then if you could get one of these microcaustic crossings in detail, then you could hope to detect, for example, the effect of a limb darkening model of the star, right? Of figuring out a bit more about what kind of star you can see. This is the curve I showed you before, the prediction for uniform surface brightness disk. As you have more limb darkening in this very simple linear model, you change the shape of a light curve. So with good photometry, you could try to tell that. Now, the interesting thing is, well, I will skip this in the time. This basically is some fits we have done with undergraduate student in Barcelona, Gaby Torralba, okay, of the data that is available from Kelly et al. Of this event, which is the brightest such supermagnified star. You could try to fit a single Cortic crossing, and it fits fairly well, and figure out if there's maybe double Cortic crossing or something. So you could start asking a lot of details about such light curves. And of course, right now, JWST can observe some of these events, and HWO will be much better at observing this. But some things we could figure out, for example, is if the dark matter is made, for example, of usually axion mini halos. The dark matter could be axions. Then mini halos would be producing some clumpiness, right, in the dark matter. This clumpiness will be very hard to see in any other kind of observation because they are highly subcritical. These subhalos will be highly subcritical. By themselves, they can't do hardly any lensing. But when they are very, very close to this caustic of the lensing cluster, then even a very small surface density can have a large effect. In this case, instead of having your light curve and caustic crossing, there will be all kinds of perturbations here, right, on small scales, time scales of weeks, let's say days, weeks, that you would have to follow this light curve, okay, due to this kind of irregularity in the dark matter distribution. If we could detect such an irregularity, then we would know something really new about dark matter. This would constrain the theories about what it is. Let me just conclude. So supermagnified stars, I think, offer these great promises for resolving stars at cosmological distances And then through this microlens and intercluster stars, probe small scale structure into dark matter in a unique way. Right, so this was discovered already and it's being observed now with JWST, but the Habitable Worlds Observatory, I think would be wonderful tool to discover this. You would also see open sequence stars because you can see at more blue wavelengths, blue supergiant stars. And because of the great angular resolution, high resolution imaging camera for this would be great with very small pixels that take advantage of the diffraction limit and so on, right, for these very faint objects. This would provide greatly improved photometry for measuring such light curve when there is a bright event like that. Okay. Of course, the ground-based telescopes can provide alerts, and then you can use HWO to follow the light curve and do great photometry. And I think it would be a very, very good probe to this kind of parsec scale of thousands or hundreds of AU scale of the dark matter irregularities, which nobody else can detect with any other observation. So thanks very much.
Questions? Jordi?
Hi, Jess Apple from Durham. So this is a really cool talk, but I have a question. So sort of on the scale of parsecs, we might expect to also see in like the intercluster light things like intercluster globular clusters. So I'm wondering how could we like break that degeneracy between this being caused by like perturbations in like axionic dark matter, very low mass subhalos, or something like a fainter globular cluster than what you could pick up in your survey?
Yes, I think these would be very different signatures. So things like globular clusters, I think they're on a much larger scale. We talk about 10 to the 6 solar masses. And also they are supercritical by themselves, or close to supercritical. These are highly subcritical things. They fill up all space. In fact, what you would see is the result of Gaussian fluctuations resulting from superposition of many such mini halos, because in a typical line of sight, there would be hundreds of them. So this is very different from any other such thing. You could also ask, for example, what if there are intracluster planets, like Earth-like objects that are result from exoplanets that are just flying out in the intracluster medium, right? Could you get confused by those? And the answer is, again, it's very different to have point masses or to have these very diffuse objects just because of the frequency at which you would see these perturbations.
Awesome, thanks.
More questions from the audience?
I just wonder if you have an estimate, a ballpark estimate for the total number of events that could be monitored over a 5-year period or something based on expectation of intrinsic rates and then the discovery step with the ground-based telescopes.
Yeah, I mean, we see that there are many such events. For example, last year there was this paper, Fudamoro et al. In HWO25, they just have an image and there is like, I think 30 variable transits, right? Most of which we think are these super magnified stars. Now, so I think the discovery rate will be increasing. What happens, of course, is that a lot of them are very, very faint. This one, what that was named Icarus, is I think the brightest one so far. So I think, if the good thing is to discover them, maybe with also these ELT or, other telescopes. Once you see a bright one, just go for it with HWO to see if you can really monitor the microcosmic crossings, right? Right now, I think it would also be very interesting to re-observe Icarus with JWST. So I think there will be enough events, but the question is, how many orbits are you going to get to monitor those over several weeks, let's say.
Okay, let's thank Jordi again. So we go to the last talk of this session. So we have Dmitry Vorobyev from University of Colorado, and he'll talk about MAGPIE, Preparatory Science Surveyor and Technology Pathfinder for Habitable Worlds Observatory.
Does it still not work?
It has worked this whole time.
Okay, that's okay. Hello, everyone.
I want to start by thanking the organizers for the opportunity to speak in this session, especially because unlike the previous speakers, I'm not really an expert in CGM physics. I spend most of my time thinking about enabling technologies and instruments to enable the missions of tomorrow. And in the last few years, my collaborators and I have been thinking about ways to observe diffuse gas from space, including from flagships like HWO25. And this talk is a distillation of some of the ideas I've been thinking about. So everybody in this room probably knows that of the three themes identified in Astro 2020, how ecosystems has maybe the broadest scope in terms of the kinds of systems that it's concerned with. And we in particular are interested in questions that are related to the conditions of the CGM, the coupling of galactic scale processes to the extragalactic gas halo, and the mechanisms that produce and recycle metals and also produce ionizing photons. And we are trying to address these questions by studying the CGM in emission. So the field of the variant cycle and life cycle of galaxies was bolstered significantly when COS was commissioned on HST. One of the first systematic studies of the CGM was performed using quasar absorption. For example, here's a figure from Tomlinson 2011 et al., where they looked at a sample of 42 galaxies with background quasars. Here we actually see a twofer. And what they showed is that these gaseous halos are ubiquitous, they're metally rich, they extend to 100 and change parsecs from the galaxy disk. And since then, many others have found similar results. At the same time, we expect these halos to be multi-scale and multi-phase. And given the complex structures that our models are predicting, even a handful of sidelines per galaxy is still going to give us a very limited picture of the spatial distribution of these halos. So we really need to study them holistically with something like an IFU. So when we observe the CGM emission, currently there are two ways. There is on the ground a handful of IFU instruments. This is VLT used, but Joe Stoff had a really nice overview of the other instruments like KCWI. With the ground-based IFUs, we can observe ionized species in the UV by about redshift 3, so during cosmic noon. And here are some examples of Lyman alpha, carbon, helium of a couple of galaxies. The scale here is, a couple of things that are in space. With James Webb, there is now an IFU that can perform similar observations at redshift 6 at cosmic dawn. And here's a map of O3, for example, for a galaxy. This is on a scale of a couple arc seconds. The field of view is 3 arc seconds for James Webb. So the good work is happening in the high redshift universe. So we know from models that the gas is extremely multi-scale with structure from 100 parsec scale all the way to the edges of the halo. We also know, highlighted in the decadal survey, that not only do we not really understand the physical conditions of CGM in terms of temperature and density, but we also don't have a good grasp on the physical processes that lead to these conditions. And as an example, we are not sure of the effect of things like cosmic rays that might have on the heating of the CGM. Meanwhile, there are models like FIRE2 shown here that show that including cosmic rays and in energy simulations leads to drastically different predictions for observables like the surface brightness of certain ions. So these predictions should be testable, and they are really best handled in a holistic IFU way. So just to survey our current capability to study the CGM in its spatial extent, I took an O6 map and I demonstrate what it might look like to current instruments if you put this galaxy at the respective redshifts. This is not to say that necessarily these things can observe O6, that's neither here nor there. It's just to show that if you take a Milky Way like Halo and you put it at redshift 6 and you put the near spec IFU on top of it, you're going to get the 3 arcsecond field of view centered on the disk, and you're going to get about 20 resolution elements across that field of view, given James Webb resolution. On the ground, a similar object will look much coarser due to the seeing limited performance of the ground-based IFUs. Nevertheless, we still learned something. If you take the same galaxy and you bring closer, by the way, I just realized that I did the math wrong. So this looked more like 400, it's about 700. I'm sorry about that, doesn't change anything. This is basically correct though. So if we take the same galaxy and we bring it to the more low redshift universe, and we put across a HWO25 notional field IFU with a size of about 3 arcseconds and a resolution of 25 milliarcseconds, well, now we're sampling the CGM on order of about 100 parsecs per resolution element. Okay. So just to survey the challenge before us, the CGM is predicted to be quite extended, reaching 100 parsecs, 100 kiloparsecs. It's relatively faint. So even though HAB worlds will have supreme resolution and pretty high aperture and high sensitivity, an IFU that produces 14,400 spectra simultaneously will still only cover a region of about 3 by 3 arcseconds if you're really maximizing spatial resolution. Now, this is impressive, but I think what this really means is to maximally use HAB worlds, it would really help if we knew where to look and we don't use this instrument to actually search for the emission itself. To this end, we are proposing creating a treasure map or HWO follow-up with a precursor science mission. So this mission would have to be sensitive to diffuse gas to achieve a reasonable SNR in a reasonable amount of time. It would need a broad spectral range in the UV, and its spatial resolution ideally should be matched to the field of view of the HAB world's IFU. What does this look like? Well, if we're aiming for a resolution of 3 arcseconds, then we could easily get a field of view of about half an arc minute by an arc minute. But to achieve the needed signal-to-noise and sensitivity, you would need a 3-meter mirror, which is kind of tough. But if we relax the spatial resolution to 6 arcseconds, then the field of view doubles, and now this becomes a 1.5-meter telescope, which starts to kind of look like a CGM-focused mid-X mission, which is maybe plausible, and something like this would observe the CGM of galaxies very thoroughly in the course of a year or something for dozens of galaxies. So mid-X's are like a whole thing, and one of the first steps that we're working on is a smaller concept we submitted to the Astro Pioneers program. It's called Magpie. It is a UV integral field IFU with 2 channels. It uses an image slicer. It covers 1,000 to 3,000 angstroms, has a field of view of 5 by 12 arc minutes. And initially, we envisioned this having a slicer with 10 facets that are each 30 arcseconds. But even at the beginning, our team was really dismayed, and they wanted higher spectral resolution to really get a grasp on the kinematics. And especially after the talks I've seen this week, we're really considering a modified design where we have variable width facets to give some higher spatial and spectral resolution, but also some broader slices to really get at the diffuse gas. With a system like this, we expect, even with conservative flux predictions, to get decent SNR out to distances like 50, 60 kiloparsecs from the disk, and really high SNR in the near disk region. And it'll cover a really broad range of density and temperature. So I'll just conclude that these types of observations, we came up with a figure of merit called spectroscopic mapping efficiency. And this is the instantaneous field of view of your system and the surface brightness limiting magnitude to achieve some SNR. So you can see that a mission like MAGPIE is really designed for this kind of work. Even something like Habitable Worlds, which is extremely sensitive, is just not very efficient due to its high resolution and necessarily smaller field of view because it's a large instrument. The price we pay for this, of course, is spatial resolution. We're only going to get 10, 20, 30 arc seconds pixels. But this is how you get sensitivity. Okay, and just lastly, while you have an IFU like this, you can also use it to map out nearby star forming regions, trying to answer some more of the cloud ecosystem questions. You could completely nail a star forming galaxy, getting the ISM and the star forming regions there, thereby kind of closing the cycle and looking at all the scales from the CGM scale to the galaxy scale to things like supernova remnants and star forming regions. So I'll just end with a summary here that we think that a way to bolster CGM science and maximally utilize a future HAB Worlds IFU is to do a preliminary mission that looks like itself a UV IFU with relatively coarse spatial resolution, but high sensitivity and high field of view. These observations are complementary to our current tools, and it would be an armed demonstration of the slicer concept, which right now seems to be like a forerunner for the HAB World IFU. And some of the collaborators on this project are in this room. They're from all over the place. Some of them spoke in this session. I'll stop here. Thank you, and I'll take your questions.
Thank you, Dmitry. Questions?
Thanks, Dimitri. This is HWO25 from Arizona State University. So I was just wondering if you could comment on the data that you'll get from Milky Way CGM while you're observing everything else. And can you sort of piece together that data to learn more about the Milky Way, where we have sightlines already?
In emission or more in observation?
In emission.
I'm not really sure what the surface brightness of the CGM gas is. So our limiting magnitude is something like 3 times 10 to minus 19 ergs per centimeter squared. If that gives you an idea.
Think about that, but that's a possibility because you could stack your data from those lines.
We have a question online.
This question is from Ethan Siegel. This might not be a relevant question, in his words, but there has been very interesting research about the role of the circumcluster medium in colliding galaxy clusters, such as bullet light clusters. What type of information could HWO tell us about the circumcluster mediums of those systems that current observatories can't yet reveal?
Yeah, wow, I really am not equipped to answer that question. I will say that I think HAB Worlds is going to look at things that have a brightness of like 10 to the minus 18 on scales of a handful of arc seconds with resolution of tens of milliarc seconds, right? If that kind of capability helps you look at those structures, then maybe a lot. Sorry.
Okay, let's thank again. So it's time for posters and coffee. We didn't talk very much about cosmic dust, but if you're interested in looking at the poster from Roberto Paradini about dust extinction, go see it. If you like absorption line spectroscopy at high resolution, ISM and applications, go look at the poster from Adam Ritchie and just enjoy your coffee. Be sure you're back at 4:20 for the continuing. Thank you very much, everyone.
Yeah, exactly.
Oh, my gosh.
Running like the most critical test on one of our projects ever right now. I screwed it up once 4 minutes ago. I ran out of like.
Right now.
Yeah, it's getting nice. So, sorry.
So Brett, how was your poster session? Nice. I mean, yes, I think people just came to
So,
me at my poster.
welcome back to the last session on cosmic origins. Our next speaker is Jan Rode. He will talk about HWO25 observatory, the nature of the first stars.
Thank you. And thank you for the organizers and to the folks who did all the work to organize the CDDs, to make this happen. Appreciate it. Appreciate the opportunity to be here with you today. I will present a summary of one of the science cases that we developed for this whole exercise. This one was co-authored by Ron Ezzedine and Jen Sobek, and we posted this on archive last month. Okay, great, thanks. What's the nature of the first stars? The first stars formed from the cloud of hydrogen and helium created shortly after the Big Bang. These first stars, also known as top 3 stars, are expected to have been massive and short-lived. They produced the first metals, perhaps the first black holes. And then these first metals seeded the interstellar medium and enabled the first low-mass, long-lived stars to form. No first stars have been found. And so their nature, their end states remain unknown. Where did they form? What were their masses? And what was the first star, IMF? How did their lives end? And what did they leave behind? They produced the first metals, but where are those today? Do any of these low mass first stars actually survive until today? Understanding the nature of the first stars is and has been one of the key points of addressing the big science questions addressed or raised by the HWO2020 Decadal Survey, new messengers and new physics, cosmic ecosystems. Today, I will share with you how the Habitable Worlds Observatory has the high spectral resolving power in the ultraviolet to identify any surviving first stars, if they exist, and to characterize the nature and the end states of non-surviving first stars by studying the metals that they gave to the long-lived second generation of stars that survive until today. So there are 2 objectives here. One is to confirm a zero metallicity top 3 star, if any exists in the Milky Way or its surrounding stellar populations. And the strategy with this is to derive the strongest limits possible on the non-detection of metal lines in the spectrum. The second objective is to derive the abundances of the metals in those second generation stars that we know exist. And these metals in these stars reflect the yields of one or very few top 3 supernovae. So you can work backward to the first stars that way. Okay, now, nothing seems to be moving forward. UV spectrum, as you might guess, is key to both objectives. That's why we're here today.
And this is because the strongest absorption lines of most metals are found in the UV. This periodic table illustrates which elements are found and where. The ones that are highlighted in some form are elements that are detectable in some way in the most metal poor stars known, ones with iron to hydrogen ratios about 6 orders of magnitude, 1 million times lower abundances than we find in the sun. That does actually say iron to hydrogen bracket notation less than -6. Elements with the red circles are ones that you can detect in the optical in these stars in sort of the best case scenario. The elements shown in the blue rectangles are ones you can detect in the UV if you have UV spectra. And then of course the ones with both symbols you can detect in both the optical and the UV. And this figure illustrates one big reason why the UV is key to this science case. The UV gives you access to a much more complete chemical inventory to constrain your models of nucleosynthesis in the first stars and have a better sense of how those stars distribute those metals back into their environment. You get C and O, you get most of the alpha elements, and the iron group elements. So here's one example of the state of the art. So this is the zoom in on a region, small region of the optical spectrum. And this compares 3 different very low metallicity stars. Bracket iron to hydrogen notation, -4 at the top, -5, and an upper limit of -7 at the bottom there. And of course, as you expect, as the metallicity decreases, the lines get weaker. So with an ideal target star and exquisite spectra, that limit of iron to hydrogen of about -7 is about as low as you can go before all of the optical iron lines completely disappear, become undetectable. There are about 10 stars with metallicities less than about -5 that we know of today. All of them have some metals, including often carbon, magnesium, calcium, sometimes iron. And these are the kinds of stars you want to study. These are the second generation stars we're after. And with optical spectra alone, your chemical inventory is going to remain extremely limited. And all of these stars are too faint to observe with high spectral resolution in the ultraviolet with Hubble. So this is the advance that UV spectroscopy with Hubble offers you. These are regions around the strongest magnesium at the top, silicon, and iron lines. Black line is a spectrum collected with STIS on Hubble. It shows a metal poor star with a metallicity of -2 for reference. The lines with different colors in each panel here represent 1D LTE model spectra for much lower metallicities. And this is what you should notice in the figure. For the top curve in each panel, that's the one with the lowest metal abundance in each panel. Those lines are still detectable. So the range of abundances that you could expect, or the range of upper limits that you could perhaps place on the abundances of these elements, are much orders of magnitude better than what you can do in the optical. You can make similar estimates for other elements. The reason that the UV is so much more powerful here is because the conditions found in the typical atmospheres of FGK type stars lead to the strongest lines of the dominant ionization state being found in the UV. So imagine what you could learn if you have much stronger constraints, 20 elements per star, rather than just sort of 5 to 8 in the best case scenario from the optical. If there are any first stars in the Milky Way that survive until today, this is how you find them. and convince yourself that you found them. Here's the other major advance that HWO offers. And this is the reason this work has not already been done with Hubble. So the figure shows the V magnitude of known metal poor stars as a function of metallicity. V magnitude is shown, and with Hubble, you're basically limited to V magnitudes brighter than about 10. With Habitable Worlds Observatory, you can observe nearly any star in the UV whose optical spectrum you can get from the ground today. Briefly, here's a description of the observational requirements. You want to observe as many stars as possible, probably a few tens would be nice. You want to be able to place strong upper limits for detections of about 20 elements per star. To do that, resolving power, spectral resolving power of about 60,000 is fine. 100,000 is probably ideal for this work based on experience. Wavelength range, let's go to 1800 angstroms. That gives you a lot. That gives you all of these metals I've shown you. 3100 at the other end bridges to the optical. You push further into the UV, that's completely unexplored territory here. Signal noise ratios are not unreasonable, 50:1 after coads and repeated observations. And none of this is going to drive the observational requirements, I think. You just want a workhorse UV Echelle spectrograph. But that workhorse UV Echelle spectrograph on habitable worlds has the potential to revolutionize our understanding of the nature of the first stars. Here's the archive ID for our science case. We welcome further endorsement, and I welcome your questions and comments. Thank you.
Yeah, those very inspirational questions. Adam?
So many questions. I think it was to you guys right there.
Yeah.
Okay.
Hi, Ian, nice talk. Sorry, Adam Ritchie from the University of Toledo. I was just wondering, is there a limiting metallicity that would convince you that you found a first star? In other words, no matter what your limit is on the metallicity, could the line just be below that detection limit no matter what? Or is there, or would a second generation star have at least some amount of metals? I don't know.
Well, you expect to find something, and at some level, the metal balances get so low that you reach effectively the same case where you have none at all. In terms of you need carbon and oxygen, that's the prediction at least, you need carbon and oxygen to be able to cool and form a low mass star below 1 solar mass that can survive across 13+ billion years. So at some level, you're splitting hairs about just a nomenclature.
Dennis?
Can you remind us where the best candidates are and say a little bit about the ultrafans too?
Yeah, so the best candidates are probably stars in the halo, right? They're accreted, probably an accreted population, or the population, as Jason told us a long time ago, probably formed in the bulge. We're probably not going to be looking into the bulge through all the extinction you get for these kinds of stars. So you want to go to the halo or perhaps the ultra-faint dwarf galaxies. All the red giant stars and known ultra-faints have been studied at this point. They all have some metals, but if you go down the luminosity functions, the main sequence or below the turnoff, it's challenging even with a habitable world. But if you find the right candidate, maybe you write the right strong proposal to do that.
So you have precursor science to identify good candidates before HWO?
I can write you the target list right now.
Other questions? Online?
No questions.
Thank you. Just speak a little bit about when you have that increase of abundance, when you have more elements with abundances, how is that going to help our current empirical models of the yields? Is that significantly going to solve good constraints? Are you going to be worried about those two enrichment events versus just one? Is there any practical constraint we will have to get out of it?
Yeah, we get, what kind of constraints we get out of this in the models by having all those additional elements. And at some level, I'm not concerned about that. That's fun for the theorists, right? To think about how many stars do we need to have contributed? Do we have a pattern for which we can find no model, no single model that can reproduce this pattern? With what you start appealing to very, very rare occurrences or superpositions, multiply enriched events, right? There are predictions for all these things in the literature now. And once you have more stars, more constraints, that's even more fun for them to work with.
Great, let's thank Ian again. The next speaker is Deep Anand from Space Telescope Science Institute. He will talk about 1% measurement of the Hubble constant with the two-run distance ladder using the habitable volume.
Advanced.
Can you hear me?
No.
Okay, is that working?
I think it switches off.
Hello. Okay, that seems to work. Thank you. My name is Deep Anand. I'm a staff scientist at the Space Telescope Science Institute, and I'm excited to talk to you today about what the distance ladder might look like when habitable world is flying. And so this is work I've done with Meredith Turbin at UC Berkeley and Rachel Beaton, who's also at Space Telescope. And so, first of all, before we get to the distance ladder, just galaxy distances in and of themselves are a fundamental quantity. You need them to provide the basis for pretty much every other astrophysical measurement if you want to turn a flux into a luminosity and angular size into a physical size. So if you're doing extragalactic science, you need to know your distances. Beyond that, they form the basis of other science like large-scale structure. So right here, you see an image of Laniakea, our home supercluster, which we could only map after obtaining tens of thousands of galaxy distances in the cosmic space program. Cosmic expansion we'll talk about, and then much, much more. In the nearby universe, within tens of megaparsecs, redshifts are not an appropriate proxy for galaxy distances because the peculiar velocities are a significant contributor. That's because galaxy-galaxy interactions will induce an additional velocity on top of the Hubble flow. And even a modest error in your galaxy distance translates to a pretty large offset in your inferred quantities. Something like 20%, which is pretty typical of the Tully-Fisher relation, or the fundamental plane will result in a 50% offset in an inferred luminosity. But thankfully now, with Hubble and JWST flying, the gold standard of galaxy distances are resolved stellar candles, things like Cepheids in the tip of the red giant branch, which can get you 5% distances. And so talking about cosmic expansion, in the last 5 to 10 years, it's become pretty clear there's a mismatch between what is predicted by the early universe, if we assume Lambda-CDM cosmology, and combine it with measurements of the cosmic microwave background, and the late universe, which is a sort of direct path using galaxy distances and recessional velocities. There's, 5, 6, 7 sigma, depending on who you believe, discrepancy in between those values. And if that tension holds, it would signal the need for new physics beyond Lambda-CDM, which is really exciting. The most prominent measurement, I think I would argue, from the local side is from the HWO's team, where they adopt a 3-rung distance ladder. So they used geometry, so parallax measurements and things like that in the Milky Way and the other nearby galaxies like the Magellanic Clouds to calibrate the brightnesses of Cepheid variables, which we can use in nearby galaxies to then calibrate the brightnesses of type 1a supernovae, because Cepheids in and of themselves are not we're not able to find them and observe them in the Hubble flow with HST or even JWST. And then so once we use them to calibrate type 1a supernovae, we can observe them out and then measure the expansion rate of the universe. And I want to sort of stress on the fact that Cepheid crowding has been a big topic, but I think with recent JWST results, I think we've resolved the issue of Cepheid crowding, and then we can firmly claim that Cepheid crowding is not the cause of the Hubble tension because the distances that we get with HST and JWST are very consistent. And so you see that little inset there showing what a typical scene with Cepheids looks like. We're able to uncrowd the region around Cepheid variables, but the distances that we get between HST and JWST are very consistent. Okay, so if Cepheids are fine, what about the last rung of the distance ladder, type 1a supernovae? And so here I think we have some remaining concerns. We're not sure about the nature of dust in other galaxies compared to the Milky Way. There's concerns about population and progenitor differences. We don't exactly know what the progenitor mechanism and behavior of the white dwarfs that lead these type 1a supernova events are. And there's also just a programmatic issue in that there's a lot of inhomogeneous photometry for the supernovae from many disparate ground-based observing facilities. A lot of work has been done to sort of standardize these measurements, but it remains a little bit of a concern. And so what if we can measure resolved star distances directly out into the Hubble flow and bypass the need for type 1a supernovae? And I think that's what we can do with comparable. And so this would be a two-rung distance ladder where you use geometry to directly calibrate these resolved stellar handles and use those out at 100 megaparsecs to measure the Hubble constant. And so not just Cepheids, I talked about the tip of the red giant branch. So Cepheids are pulsating variables. The tip of the red giant branch is the truncation of the red giant branch due to the helium flash event, which has a standard luminosity. And then there's also this third population, these carbon stars or JAGB stars. And these are all actually, they come from sort of different age stellar populations. And so in that way, they live in different parts of the galaxy and they provide a good cross-check on each other. And if you're clever about designing your observational program, you can actually get the data for these three different distance indicators simultaneously. And so here's an image simulation that Meredith produced of what a scene at 100 megaparsecs would look like. The top panel, I work on the ACS instrument team and I love ACS, but you can't see much of anything there. But with habitable worlds, we can resolve Cepheids at their minimum and maximum light, phase them, detect them, and measure period luminosity relations at 100 megaparsecs. So taking into account the expected uncertainties using the HWO's model, we think with 24 galaxies at 180 to 100 megaparsecs, we can get a 1% measurement of the Hubble constant. And then if you're concerned about large-scale structure systematics, you can repeat the experiment multiple times in different quadrants of the sky or different regions of the sky to test those. And that 1% measurement, 1% is a nice number, but it's also physically meaningful because the theorists are really busy about, what kind of models, what kind of new physics you need to resolve the tension. And a 1% measurement allows you to actually discriminate between a lot of these different cosmological models. So what is the new physics that we might need? And so that's a really key aspect. We're not just going for 1% because it's a nice number, but we think it will be useful in determining what kind of new physics exists. And going one step further, actually, so with a three-rung distance ladder, you're limited to looking at Cepheids in galaxies that host type 1a supernovae, which is only a small fraction of overall galaxies. But if you have a two-rung distance ladder, you no longer need to look at galaxies that have type 1a supernovae. You can just look at any galaxies that have these stars, which are pretty much all massive young star-forming, or all massive star-forming galaxies. And so you can actually preferentially target galaxies that have lower crowding. And so here's an example that should be on the archive next week or the week after, but NGC 3447. And so the left image is what we see with HST, and the right insets are actually seen with JWST. And so the bottom is a typical Cepheid scene. The Cepheids are in the disk of galaxies. There's crowded, there's red giants, there's AGV stars everywhere. We can resolve them, but it's a little bit messy. Now, in the tidal dwarf, that's the companion to it. We see a ton of Cepheids, And there's no red giants, there's no old population, there's no intermediate age population. They're very, very clean. And so we can preferentially target these regions of the worlds. And so I'm talking about looking at stars at 100 megaparsecs. I think actually some of the most challenging observations with habitable worlds are going to be at the right end, because we need to do the calibrations of these stars in the Milky Way and the LMC and the SMC, where these stars are very bright. And so we're going to need to be careful about getting developing clever techniques to get around the nominal saturation limit of habitable world. So whether those are neutral density filters or diffusers or scanning modes like we use on HFC, I think that's going to be a huge necessity. And lastly, as a little bit of an aside, so Cepheid, TRGB, et cetera, these are great for massive galaxies, but what if your galaxy, it doesn't have enough of those stars? So with things like Rubin, we're going to find a ton of low mass dwarf galaxies in the local volume. And if you want their distances, if you wanted to study them in detail, you can't use these methods. Here's a plot from Savino et al. You can see that this is a plot of RR Lyrae distances versus TRGB distances, and you can see the TRGB distance actually break down at some point because there's not enough stars on the red giant branch. So we can use RR Lyrae instead, which are 10-year low mass stars that are much more plentiful, and get distances that way. With HST and JWC, you can get out to maybe 1 or 2 megaparsecs, but with habitable worlds, we'll be able to cover a significant fraction of the local volume at 7 to 8 megaparsecs. And yeah, so that'll conclude. So galaxy distances are really important quantities, and they will be if you want to study nearby galaxies. A 6-meter habitable worlds observatory is going to allow a 2-rung distance ladder where we can use geometry to directly calibrate stellar standard candles and use those in the Hubble flow to measure the Hubble constant. We're going to have to be careful because we're asking for a huge dynamic range in the observations here from 7th to 33rd magnitude, basically. So that's going to require a lot of careful work. And then our Lyrae stars are going to be also useful for measuring distances to low mass galaxies, but the other methods unfortunately just fail us. I'll put another pretty picture and take sheets.
Scott Gowdy, Ohio State University. This is great. I think, a 2-rung distance ladder is fantastic. But in reality, you're still going to do the supernova, right? So can you give me some insight into how doing the supernova and having redundancy in these galaxies that are in the Hubble flow that have both supernova and Cepheids will help both the Cepheid anchor and the supernova anchor, which itself might be important for cosmological studies at much higher redshift?
Yeah, so I think the supernova are going to be useful, and then Roman will be good for that too. But that I think are going to be more used for studies of like dark energy and evolving dark energy. I think with the Hubble concept, we don't want the supernovae in this. We're trying to get rid of it basically. So yeah, at higher redshifts, the supernovae will help with like the nature of dark energy, but I don't think they're going to help here. We're trying to get rid of them for this specific problem.
More questions for Deep? I don't see. If not,
Up for one.
Yeah. So do you have an estimate for, you have something like a total time or a total duration of this project?
Yeah, I should have maybe added that in here, or at least put the link. So read our SCDD, it has a lot of the details, but it's about, for the Cepheids, you want 12 EVEX, 1 hour each, so 12 hours per galaxy, and if you want to do 24 galaxies, it's a couple hundred, 200-300 hours. So it's a big program, but it's not unreasonable. And then that same integration time will give you the JHGB and the TRGB stars as well.
so let's thank Deep again. So next speaker is Thaisa Storkeep Bergman from Instituto de Física, Universidad Federal de Rio Grande do Sul. And she'll talk about the starburst AGN connection along the history of the universe.
Hello, everybody. Can you listen to me? Okay, I'm going to talk about this. I included the HWO connection, so the AGN starburst HWO connection across the universe. So this work is within my group, HNIF's group, AGN Integral Field Spectroscopy group. We have been doing IFU studies for 2 decades, more or less, and we have studied AGN feeding via interactions, inflows, AGN feedback via outflows, and in this talk I will concentrate on our results on stellar populations. And this is the group that has been working with me. Okay. This is a review that I wrote together with Sharp Miller in 2019. In this review, we discussed the feeding of AGN across several scales, from extragalactic down to nuclear scales. And I want to concentrate today on these nuclear scales between 10 and 100 parsec, where we found in many AGN, active galactic nuclei, inflows in nuclear spirals. This is a very nice one, but there are others. And the main result of these studies, well, another one, we have found inflows also recently in molecular gas in AGN, in work led by Bruno Dallagnol de Oliveira, where the green contours, this is 1 kiloparsec, the inner 1 kiloparsec on 4 AGN, and the green contours are molecular gas, cold molecular gas observed in ALMA, and the red contours are ionized glass, so we see outflows in all these galaxies, and the outflows are anticorrelated with the CO. CO is anticorrelated with the O3 emission that we know are outflows, are due to outflows. So we see the cold molecular galaxy also feeding the supermassive black hole in this AGN in circumnuclear disks. The key point in these inflows is that we are finding mass inflow rates that are higher than the black hole accretion rate. Okay, so the mass is going in, but the mass accretion rate, or mass inflow rate, is higher than the accretion rate to the AGN. So where does this mass go? So this accumulates in the nuclear region, and there they are filled for circumnuclear star formation. Okay, so we have studied star formation rates around AGN. And in AGN, you cannot use the gas. For example, H alpha, everybody uses H alpha to calculate the star formation rate, but you have to assume that it's ionized by stars. In AGN, it's ionized by the AGN mostly. So in a work led by Rogério Riffel, he calibrated, he obtained the star formation rate from the stellar population, from the synthesis of stellar population. So from stars younger than 20 mega years, you can have a star formation rate calculation. And we found a correlation between the star formation rate from stars with the star formation rate from the gas. So we can use the stellar population to obtain star formation rates in AGN. So one work that we have recently finished was to use 300 AGM and a control sample of approximately 500 control galaxies from the MANGA survey. I don't know if people are familiar with the MANGA survey. It's a survey, integral field spectroscopy of this long digital sky survey. So we observed, we used this method to obtain the star formation rate in AGN. I missed one. Okay. So one result that we found is that within the inner kiloparsec, the inner part of the galaxy, we find the star formation rates in AGM stronger than the star formation rate in the controls, about 2 times stronger, you know, the average, the mean actually. Okay. And also she put Lara put this the star forming the AGN and the controls in the star forming main sequence, using all MANGA galaxies, star forming MANGA galaxies. So what we found is that the AGN are close to the main sequence, a little bit below, but the controls are a little bit more below. Even this is integrated over the whole galaxy. So we see the same trend. The star formation rate in AGM is stronger than the star formation rate in the controls. So what we concluded is that the ongoing activity in AGM is more related to the increase in star formation rate than to quenching of the star formation rate. The usual assumption is that the AGM quench the star formation, but we find that during the activity, it's more connected to the increase of star formation rate, the AGM, the nuclear than to the quenching. And then, can we find the starburst, this young star, because the star formation rate implies that we have young stars around AGM. And we have found in a few cases, and I intend to pursue this more. And for example, this is one case that I observed a long time ago with HSP, STIS spectrum, where I found a red starburst within 9 parsecs, 10 parsecs from the nucleus. So a very nuclear starburst around the AGM there. And there are a few other cases of where we even see in the UV, we see absorptions from the young star O and V stars. Okay, and this is, then I recall also a model from a collaborator, Keiichi Wada, that he proposes that when you have an HM and you have a torus, the mass, the molecular torus, that's part of the AGM, you have conditions to trigger star formation. You have molecular gas, you have the condition to trigger star formation. Okay, then, and then I will pass very quickly. I found some evidence that in narrow-line Cipher-1 galaxies, you can reproduce better the UV if you include a starburst. And also, even in the little red dots, I tried to fit the UV upturn of the spectrum, and I could fit by a very young starburst. So this is ongoing work, and I need to wrap up. So this is the fitting of the UV with starburst, and with a accretion disk in the optical. And what my conclusions are is that, okay, because the mass inflow rates to AGN are higher than the black hole accretion rate, we have excess gas around the nucleus, and this can form new stars. And in nearby AGN, we can see starbursts in the UV within 10 to 100 parsecs from the nucleus. So the HWO integral field spectroscopy could be used to observe AGN in the rest UV across the history of the universe, because the angular resolution, well, because of the UV capability, UV integral field spectroscopy capability, and the angular resolution can probe the inner 100 parsec across almost all distance. And finally, yeah, and also we can use the coronagraph. Yeah, somebody told me that we can use the coronagraph together with the integral field spectroscopy in the UV. And this would be ideal to look for type 1 AGN where you have the glare of the nuclear source. So we can perform this study also for type 1s. And I found this paper, somebody suggested me in the Slack, ran it all that use the STIS coronagraph to do this kind of study where you can see not only star formation, but you can see all kinds of structures in type 1 AGN that are blinded by the glare of the nucleus. Okay, thank you very much.
Questions for Lisa?
Hi, guys. Yeah, thank you for the very nice talk. So for the infamous layer dots, what kind of star formation rates and stellar masses can you find with your fits?
Yeah, this is still preliminary, but I'm doing with 1 mega-year age with starburst 99, but I have to do these calculations. I didn't finish. I just tried to see if I normalize it to see if I could fit a starburst, and I tried several starbursts, and try the fit using minimization, T-square minimization, and the best fit in the UV is always the youngest starburst. If I put a little bit older, I don't get a good fit. So I think I'm very convinced that we are seeing these starbursts, and I forgot to say that we have the UV capability, and we have not explored so much the UV in the AGN. I think that the UV brings much information that we can explore with HWO.
Joe, right behind me.
Yeah, thank you. On this possible triggered starburst from the AGN activity, I wonder if you've tried to reconcile the stellar populations that are produced through these, episodic starbursts, given estimates of duty cycles and and AGN active lifetimes against to more normal galaxies that maybe aren't exhibiting activity at the current observed moment.
Yeah, the idea is that the accretion is episodic, and when you have matter going in, you have some matter accumulated in the torus and then form stars. So not sure if I answer your question, but I think that when we see the mass inflow rate we calculate is always higher than the accretion rate to the AGN, because from the luminosity of the AGN you can infer the accretion rate. But when we see the inflows, it's usually much higher inflow rate. So where does this gas go? So I think this is the reasoning that I'm trying to put forth. Yeah, and I think we are overlooking, maybe because of the spatial resolution. We didn't look so closely. I think HWO is a good instrument.
Thanks. Vivian?
Very quick question, thanks, Teresa. Just wondering, for the inflow rate that you calculated, and so the gas that's coming in, and you said it's larger than the black hole accretion rate. So does that difference account for the star formation that you see, or could there still be like a reservoir of gas that's just waiting, sitting around waiting for the black hole to eat it up?
I think it is the difference. The difference is orders of magnitude. So we see the circunuclear disks, but we begin to see inflows also in the circunuclear disks. So I think, and the circunuclear disks, have a lot of molecular gas that won't too much to feed the AGN. So I think they are going to result in star formation. Yeah, it's more like I don't make a precise calculation. I think it's the next step of this work to do precise calculation also for the little red dots. But you know, the scenario and presenting a scenario here. Okay.
Thank you. If there is time for a quick question.
That's a great talk, thank you. This is more of a comment than a question, but one of the challenges we found in the activities of the evolution of the elements working group over the past year and a half, where people are assuming where you're going to have diffraction limit. I want to see a raise of hands. How many people here, and Caleb knows exactly what I'm talking about. How many people here assume when you're calculating your diffraction limit, assume that you'll be diffraction limited in UV? No one? People are afraid. Question, I shouldn't have set it up like that, guy. No, but you know, so we have a lot of Hubble users here, right? And you know what happens to the PSF as we get to the UV degrades. And so that sets up a lot of challenges. So just have to be very aware. Steve, did you want to say something? You look like you're about to say something.
Yes, I would. I would like to comment that in fact, it would be great if we could be diffraction limited in the UV. And I just had to say that because mainly because the possibility, the exquisite optics needed for the coronography might lead to the possibility of this becoming a reality. So it's something that needs to be studied, and I encourage somebody to study.
Yeah, and that's the point, that we can't assume that we're gonna.
No.
It has to be an explicit ask. So the assumption is that, you know, you're gonna be diffraction limited at what, 5,500 angstroms, right?
6,000 or something like
6,000.
that, yeah.
Why are you looking at here?
Oh, it seems pretty high to me, right?
Yeah,
But you want to be 5, I think.
okay, yeah, no, in the V band, you're diffraction limited at the V band, basically.
Yeah.
And then, you know, if you want diffraction limit, if you wanna have a diffraction limit in the UV,
Okay.
that's comparable, we have to ask for that.
Oh, okay. But it's not 0.01. Yes, no. It's it's hard to get to 0.01.
Thank you. Perhaps we can continue then later. There's a little bit of extra time if you want to continue and discuss. Thank you very much. Let's thank Pace again. The next speaker is Kalina Netkova from Johns Hopkins University, and she'll be talking about revealing the redshift evolution of dust attenuation in galaxies with hub worlds.
Also, it's.
You all hear me, right? Yes. I see one thumbs up, so thanks. Okay. Well, thanks everyone for being here. My name is Kalina Netkova. I'm a postdoc at Johns Hopkins University, and I work with Martha Polsky at the Space Telescope Science Institute. And before I get started, I just want to say a big thank you to the UV Candles team. They obtained very deep F275W imaging of 4 of the 5 candles fields, and this is really the basis of the work that I'll be presenting today. And so today I'll be telling you about revealing the redshift evolution of dust attenuated galaxies and how HWO will really revolutionize this area of research. And so I wanted to start from something very simple, and it is that galaxies look different in different filters, right? So you can see here, this is the same galaxy shown in the bluest filter on the left, and then the reddest filter in the right. And you can see that you begin to pick up different features in these different filters. And these are all with HST. Yes. Okay, and so just to give you a little bit more information here, this is the same galaxy. You can see here the rest frame wavelengths that these filters correspond to, and you can see that in the bluest filter, you're very sensitive to the elongated disk structure. In the reddest filter, you're picking up the central bulge. And so what causes this? Well, one explanation is that galaxies grow from the inside out. You can imagine star formation happening in the galaxy. As time goes on, the blue stars are going to die off, and you're going to be left with a redder center. And the star formation is now going to occur in the outskirts of the galaxy, leading to a situation in which you have a red center and blue outskirts. And so you can imagine how this kind of scenario would result in imaging that looks like this. What about so could this instead be centrally concentrated dust here in the center that is attenuating the light and causing the centers of these galaxies to appear redder than their outskirts? And so one thing that you can do to begin to address this is measure the sizes of galaxies in the UV and optical, where you might expect that in the UV, the galaxies will appear larger, and in the optical, they will appear smaller. Okay, so we have a fantastic way to measure sizes. So when I say size, I really mean half-light radius. This is the radius at which half of the total light is emitted, shown here in this cartoon that you can see. And we are fitting the wavelength using a multi-wavelength approach. So these are all ground-based filters now, but we have a simulated galaxy for which we know the exact size. And these sizes are shown here as X's. And in purple, I'm showing you what we get when we do single band fitting. Here we've made the H band particularly noisy, just to understand the effects of low data. And we've also fit this using our multi-wavelength approach. So you can see that the green lines up much better with the simulation results. So doing this and measuring the sizes of every single galaxy in the UV candles fields. Here is our results at redshifts 1.5 to 2. I'm plotting here on the y-axis the radius measured at 1500 angstroms. On the y-axis, we have stellar mass. And the fit to these data is shown here in purple. This is the UV mass size relation. And in red, I'm showing you the same thing, but we now measure the size in the strained optical. And you can notice that the UV slope of this relation is steeper than that of the optical. This tells you that these galaxies are larger in the UV than in the optical, which is consistent with this picture that I showed you before. And in fact, if we now look at all of our redshift ranges, you can see that the UV relation is steeper than the optical at all redshifts. And what's most interesting to me is that the two redshift bins where you have the largest difference in the slope are also the two redshift bins where you have the highest dust accumulation. So you can see that there's more red points in these two bins than in the others. And this is also where you have the most different slopes. So this might be indicative of dust playing a significant role, but to really understand if this is driven by inside out growth or dust, we need to turn to simulations. Oh, okay, so we use the Vela simulations. I want to thank Swara, who's all the way back there, for recommending that we use these simulations. They're fantastic for a variety of reasons. But the reasons why I am really excited to use them is because there exist publicly available mock images of galaxies where the effects of dust are included, shown here, and where the effects of dust are excluded from the simulation. So this is just how this galaxy would appear without any dust. And each galaxy here, each row is the same galaxy under different orientations. And so in red here, I'm showing you the ellipses that contain half of the total light. So the radii in here would be the half-light radii that we're measuring in size. And you might notice that the images with dust have larger ellipses than the ones without dust. And this is because if we take a surface brightness profile as a function of radius of a galaxy that has dust, we might expect that the center will be attenuated, it's going to be less bright. And it's also going to be less bright in the outskirts. And this is consistent with what we're seeing. These galaxies that don't have dust, they're much more extended than the ones where dust is included. And if we integrate under the curve and find where this integral is equal to 1/2, thank you, this is going to give us the half-light radius, and you can see that with dust, we're measuring a larger half-light radius than without. Okay. And so let me take a second here and just explain the axes. So on the y-axis, I'm showing you the difference between the UV size minus the optical size normalized by the optical size. So this is just the difference in size from our simulations. On this panel, I'm showing you the dust-free simulations, and on this side, I'm showing you the dust-attenuated results. And so you can notice that in the dust-free case, the difference between the two radii are consistent with 0. This is telling us that when we exclude the effects of dust, the optical and UV sizes are consistent. And when we look now with dust, we see that we have this upturn where the galaxies are much larger in the UV than in the optical. Okay, and so what do the data look like? So here are the UV candles results. Again, this has the same y-axis as before as a function of stellar mass. And you can see the same kind of upturn in the real data where the UV sizes are larger than the optical sizes. And here are our simulations with dust. They are bang on, and they match really well. And so where can we take this with HWO? So I know we've been talking a lot about the resolution that we want for the spectroscopy, but I want to really emphasize how great it would be if we can get this to slightly bluer wavelengths. If the bandpass can be 100 or 150 nanometers, that would be fantastic for the science because it would enable us to look at the UV of redshift 0 galaxies. And so if we do that, we can extend the same kind of analysis to lower redshift. And thanks to HWO sensitivity, we can look at lower mass galaxies. And so I just wanted to draw this comparison where here I'm showing you a UV candles galaxy that we measured the size of. And here's a redshift 0 galaxy. And so we can begin to look at dust on a resolved scale and really understand all of the results that I showed you. They assume that dust is centrally concentrated. Is this really the case? We can find out with HWO. Yes, and so this will be great for a lot of reasons. So I just want to conclude. I showed you that the slope of the UV mass size relation is affected by dust here. That I showed you that the presence of dust increases the effect of radii of galaxies. And I showed you that dust alone can account for the differences between the rest-frame UV and optical sizes of disk galaxies. And I'm very excited with HWO. I think it's going to absolutely revolutionize this area of research. Thanks so much. Happy to take questions.
How impressive with the effect of dust on galaxy. And really, as you mentioned, the of this galaxy. Question for Nina. Online, do we have any questions? Are we shy? There was something in your web slides that you wanted to show, but you had to wait until you didn't have time.
Let's see, one thing that I'm really interested in was understanding if, let's see, if the dust is really centrally concentrated. And so one thing that simulations assume is that the distribution of the dust traces the distribution of stars. And so here I'm showing you two different filters. So I think this one, yeah, so this is the F275W that was obtained by the UV candles team. And here I'm showing you the H band. And I'm showing you the same galaxy face on, edge on, and sort of 45 degrees on. And I'm showing you here is the surface brightness profile. And if you look at this residual, so the residual is the difference between the case without dust and with dust, and so it tells you how much light is being attenuated. And all of it peaks in the center, all right? And so what I want to know is whether this is representative of real life galaxies. And so if I can know that, that would be great.
There are nearby galaxies where we know how the dust is distributed. There are far infrared images. You could take them, scale them to what they would look like at redshift 0.5 or 1 or 2, whatever you want to do. The dust goes with gas, not with stars. So
yeah, and it's also clumpy, and so that's something that's typically not included in simulations.
yeah,
So
some approximations are better than others. That's all I'd say.
yeah, no, you're absolutely right. Thanks so much for that comment. But yeah, but measuring the UV properties for redshift 0 galaxies would be hard, and understanding this difference in size, I think, will be really.
Galaxy images. There are galaxy images of nearby galaxies, right, in the near UV?
Yes. Yeah.
What will be the advantages with the hub worlds with respect to the current images that are available?
Right. So I mean, so I think the imaging is going to be much higher resolution. So that's going to give you the ability to really probe what's going on these very small scales, right? And if we can go bluer than this, then I think that that's really going to open a lot of comparisons that we're not currently able to do.
Thank you. Are there more questions for Kalina? If not, then let's thank Kalina again. The last speaker of the session is Fab from CFA. He will talk about exploring the quiescent black hole population of nearby galaxies with hub worlds.
Okay, hi everyone, good afternoon everybody. I'm Fabio Gucci again from CFA. And today I'm going to present a science case that we developed in the AGN steering committee for HWO, which was chaired by Vivian, you, Chris Packham. And so this is mainly a conference about exoplanets. So the question is, why should we care about black holes at all, right? So let's see why black holes are very important on very different spatial scales and for very different environments in the universe with this very short video. So black holes, first of all, are important at the very smaller scales for testing general relativity, and also mergers between black holes create gravitational waves, of course. At larger scales, accretion disks transform matter into energy, and also these are important spatial scales for tidal disruption events. Now, going at even larger scales, jets and outflows have a very important feedback on the galactic medium, the interstellar, and the intergalactic medium. And even at bigger and bigger scales, so megaparsec or even gigaparsec scales, black holes seeded galaxies in very early universe. They started their coevolution with galaxies, and eventually at the gigaparsec scale, they led to the reionization or contributed to the reionization of the universe. So these are all the reasons why black holes are important for the evolution of the universe. So in this talk, in this science case in particular, we focus on black holes coevolution with galaxies. So there are several properties that the mass of the central black hole correlates with. So one of those is the MN star relation that states that on average, the black hole mass is about 1/1000 of the stellar mass of the host. So basically bigger black holes in bigger galaxies. Now, we have seen in the last few years several departures from these general scaling relations, both at high redshift and in the lower redshift universe, so local universe. In particular, in the high redshift universe, we are seeing the Lioret dots that I was mentioning before. That's another full chapter. So generally speaking, showing many black holes that apparently are significantly lower massive with respect to the local NM star relation. In the local universe, there are several instances of black holes that seem to be significantly undermassive with respect to the local NM star relation. So, why is this important? One of the main reasons why this is important is for the black hole seed problem. So, what are black hole seeds? Black hole seeds are the first population of stars, the first population of black holes that was formed around redshift 20 to 30, so a few hundred million years after the Big Bang. So why are they important? Well, for a few years now, we've known of the presence of supermassive black holes or quasars, so 10 to the 9 or even above mass black holes, even a redshift higher than 7. So when the universe was significantly younger than now, like less than 1 billion years old. Now, to form these very massive black holes, you need to start from smaller units, redshift 20 to 30. So you have approximately 500 million years to form these very, very massive black holes. One possibility to form these black holes is through light seeding, so as remnants of the population tree stars, so the first stars that were formed. And typical masses in this case are 100 solar masses. And in this case, you need to go through a very rapid growth to form the quasars at redshift 7. An alternative is heavy seeds, typically 10 to the 4, 10 to the 5 solar masses. And in this case, you can be more relaxed in how black holes grow. So how do we understand if heavy seeding occurred? Because we know that light seeding occurred because the first stars formed anyway. So in other terms, how do we know how baby black holes turned out to be like very giant black holes a few hundred million years later? One possibility is indirect methods, in particular study the combined properties between the central black hole and the host galaxies. So in particular, in the dwarf galaxy regime, so typically 10 to the 9 solar masses or less, these are very important because they keep remnant signatures of the seeding that happened at much earlier epochs. This is because dwarf galaxies don't have a significant merger history, so they keep or retain down to low redshift some signatures of seeding. And in particular, several studies show that if black holes are significantly overmassive in local dwarf galaxies, they could have been seeded with heavy seeds, or in the other case, if they are significantly undermassive, they could have been seeded as light seeds. Now, what's the role of habitable world observer? I changed the planet with a black hole. So we propose the science case basically to dynamically detect the presence of quiescent massive black holes. So these are massive black holes, 10 to the 5 or above, solar masses that are not accreting, so they're not shining, so you cannot see them in any other way, at the center of local dwarf galaxies, and we do that by measuring the velocity dispersion of stars via optical absorption lines. These are very standard techniques that are used in the very local universe. So HWO with, for example, 8-meter configuration allows a very large parameter space in the black hole mass vertical axis versus stellar mass horizontal axis. So far, we can basically study until 10 to the 6 or 10 to the 7 solar masses approximately, while HWO will allow to study black holes in local galaxies that are much lighter than that. So why is HWO so special about this? Of course, because it's angular resolution. The HWO is able to detect, as we've seen many times during this conference, the single planets in solar systems of at a distance of several tens of light years. And if you think about this, this is very similar to see the movement of single stars around a dark object. This is basically how a Sagittarius star was. The black hole at the center of the Milky Way was confirmed to be a supermassive black hole. So right now, with HST, for example, in DLT single configuration, we have typical angular resolution at 50 milliardsecond, but with HWO at a distance lower than 10 megaparsec, for example, with 20 milliardsecond, or even better, 10 milliardsecond, we can really probe of dwarf galaxies where seeding mechanism have a very important imprint. So how does the angular resolution affect the science case, or what we can achieve with the science case? So the current state of the art is this. We can observe dynamically within about 10 megaparsec about black holes of 10 to the 6 solar masses or above, of course. Now, with a higher and higher angular resolution, we can reach enhancing, enabling, and breakthrough capabilities for HWO. And this corresponds to correspondingly to 1 sigma, 2 sigma, and 3 sigma departures from the standard relation, assuming the dispersion in the relation itself. So this translates into enhancing and enabling and breakthrough capabilities for UV and this multi-object spectroscopy. These calculations are particularly for the Taussium-2 triplet, and you can see what are the different angular resolutions that we need here. So this plotting instead compares what 2 different versions of HWO, 6.5 meter and 8 meters, would compare against the currently available telescopes, HST and JWST. So this is on the vertical axis, the minimum black hole mass necessary that is visible by the different telescopes at different distances to detect the radius of gravitational influence. So when a star feels the presence of the central massive black hole. So as you can see, even in the 6.5 meters configuration, HWO has a factor of 3 of improvement over JWST. And in the 8-meter configuration, we gain an entire order of magnitude in lighter black hole masses. So there are plenty of galaxies that we can target. For example, in this plot, I'm showing the about 600 galaxies, mostly dwarf galaxies that are within 10 megaparsec. As you can see, the standard, the classic, the average stellar mass is about 10 to the 7, 10 to the 8 solar masses. So these are like dwarf galaxies. So as a summary, we saw that there are detections of both overmassive and undermassive black holes in the high redshift and in the low redshift universe. These populations, especially in the dwarf galaxies, especially in the local universe, has very important consequences for constraining the population of black hole seeds. And HWO, in particular in the 8-meter configuration, can detect the presence of quiescent black holes in down to 10 to the 4, 10 to the 5 solar masses. So in the last 10 seconds, I just wanted to give a shout out of the SIG, so the newly formed science interest group for HWO. There are several chairs here, including me, Vivian, and other 4 people here. And Joe is there, actually. And yes, we just started the work. This is intended as a interface between the community and the program office. So come chat with us, use the QR codes, sign up for the mailing list, and all together we can make a even more community-driven mission. Thank you.
Fabio, questions for Fabio?
Really nice talk. I noticed that plot of black hole mass versus distance that you just showed in the last couple of slides. For relatively massive black holes, we can see an awful long way, right? A couple hundred megaparsecs, it looks like. Have you thought at all about, probing maybe the luminous or ultraluminous infrared galaxy population and getting direct black hole measurements for those kinds of objects as well?
Yeah. Yeah, absolutely. If you go up in a black hole mass, you can go very, very far, like 10 to the 9. Even with with 6.5, you could reach like almost 1,000, almost a gigaparsec at that point. So the number of galaxies that are available within 1 gigaparsec is like huge, for sure. Yeah, so that would be, and as you were saying, this method is particularly powerful for black holes that are quiescent. They are not accreting, so we cannot see them in any other way. Yeah.
Great, thanks.
More questions for Fabio?
I was wondering, news with extreme AO with the super resolution that they have now would be how far you are from what you need using an instrument like Muse in that configuration.
So you're talking about adaptive optics.
Extreme AO, yes.
So there's that's a great question. In the science case, we made an entire paragraph comparing in the science case document. We made an entire paragraph comparing why HWO in some cases would be much better than ground-based adaptive optics. For ground-based adaptive optics, you need a guide star, so it needs to be pretty bright, pretty close, so that limits the number of targets. There is also an issue of the strand ratio that you can get with adaptive optics versus this, which has basically no limit in the strand ratio. So there are several cases. Most of all, as I was saying, the non-requirement of the guide star, so that expands like usually the galaxy number that you can use. But also adaptive optics is pretty good for this.
More questions for Fabio? Yeah.
Hi, Ron Gamble from Goddard Space Flight Center. One, I thought this was a really great talk, and it kind of drew me back to Vivian, your talk this morning. So I wonder, and I'm very curious about whether or not HWO will be able to kind of allude to more insight into the mass gap problem between like intermediate mass black holes and the supermassive.
Yeah, that's a great question, and the mass gap is a very important problem right now because we are pretty good at finding supermassive black holes that are creating a lot of mass. We are reasonably good at finding X-ray binaries, so small black holes, at least if there is a binary there, if there is a star, we can see them. But intermediate mass black holes, say 10 to the 3, 10 to the 6 solar masses, that's really a mass gap that we're not good at all right now, because these are typically smaller galaxies. These smaller galaxies don't have a large mass of gas available to be accreted. So they are basically most of them are very quiescent. Some of them may be not even at the center of the galaxy, meaning that these galaxies have such a small gravitational potential that the central black hole may be not really central, meaning that they're just wandering around. And that makes it even more complicated to find them because, first of all, they are not at the center, so you don't know how to see them. Then second of all, the gravitational potential not at the center is even lower, so you don't have gas, so they're not accreting, so it's always the same problem. So yes, if we can find them with velocity dispersions of stars with instruments like the HWO, that would be very transformative for like filling the mass gap.
Yeah, so I'm not an observational person. I'm like pure theory. Yeah. So I guess I wonder, what lessons can we learn from theory to kind of inform the observation for HAP worlds? Right. That's kind of like where my idea is going.
No, so theory can tell you that for the you're talking about the gap, the mass gap, right? Yeah. So theory can tell you that as I was saying, these black holes mostly accreting in ADAF mode, so advection dominated accretion flow. So the STDs, that the spectral energy distribution that we can find are very different for like highly accreting supermassive holes like quasar. So we expect like lower X-rays, lower radio, typically optical emission accretion, so optical emission, optical infrared emission, etc. So the SCDs are very different. They may not be at the center, as I was saying before. You can actually calculate, given the gravitational potential of the galaxy and the mass that you expect, given standard relation, which can be wrong, as I was saying before. You can kind of tell what's the volume where you expect. But this is a Brownian motion, it's not at the center, it's just wandering around a little bit. So you can kind of expect where to find them, but it's very hard to find them. That's why we typically don't find intermediate ones at all.
Thank you. More questions for Fabio? Let's thank Fabio again. It's almost all for the day, but we have a little bit of time, and I was wondering if some of you had questions before for the other speakers, if they're still around. That would be, we could have a little bit of time to bring those questions up if you wanted. I have one for Joe and maybe for the people that worked on the imaging of the supergalactic medium. That's very exciting. But what are the prospects for worlds to be look at? What speed would we need to go?
Yeah, it's also.
Thanks. Yeah, so I would like to defer to someone in the room who has actually looked at this and did a poster on this very topic, Farhan Hassan. What do you think the prospects are, Farhan?
Good. Thank you. Yeah, especially after talking to you about it. Yeah, I think we're looking at like surface brightness levels of like 10 to the minus 20 square per second. It's totally doable. Probably need a bigger field of view. So yeah, you gotta have. I think your number was like 7 by 7 arc minutes field of view or something. So we need something a little bit bigger, maybe like 20 by 20 arc minutes. But yeah, if you could do the mosaic instantly, like build like a bigger range, that's also doable. But yeah, we don't need high spatial resolution. On the order of 100 pulsar spatial resolution is good enough to map elements.
So yeah, this is probably a project for the MOS node, not for the view, where we can get these larger fields of view and for going to slightly higher redshifts than what I was talking about. Obviously, you get much larger physical scales. So even if we were to go to redshift 0.1, that automatically this 7 arc or 8 arc minutes would give you much larger physical scales. And of course, thinking about stacking experiments, if you want to reconstruct the cosmic web, like if you want to do it the right way using slime mold, then you could actually, every single pointing gives you photons that could be thrown into a stack to reconstruct the cosmic web to do, the filament cosmic web imaging that way.
Thank you both. I'll go check out your poster. Are there other questions that were asked?
There is a question online, and this is for the SIG leads. And we think we might have a partial answer in the Slack, but we'd like to know for sure. So for the SIG leads, what is the difference between cosmic origins and physics of the cosmos?
You want to take it again or someone?
I can, okay, let's see, Ron is the best person to take that.
I think that's the main question.
That's the wrong question.
Happy to represent. So it's basically answering the different, one of the three questions. Are we alone? How did we get here? How does the universe work? So cosmic origins is trying to answer that, and physics of the cosmos is trying to answer how does the universe work. And they're kind of split, but there is some synergy between the two. Yeah.
Okay, so,
More questions?
Want to add something to this?
yes, well, really, actually, maybe a question for Stephen a little bit, because we were just talking, you know, so scared. We were just talking about, actually figuring out diffraction limit and, do you think that there's a need to potentially start or have a science analysis group about this? Because this is what the SIG is for, and we're listening.
I think I'm sorry. Yeah, I think this is the sort of thing of like, for Roman, you build a coronagraph and you don't drive anything with that, but you're going to test it. So this is like a test case for you might want to investigate it to see whether it's going to happen, but you don't want to use it as a driver. You want to use a very conservative driver that you know you can achieve. And then if it happily comes out to be better than that, then we'll take it. But yeah, and it would be nice to put a little bit of effort into, trying to understand why you get the big wings on as you go into the UV. And it has to do with surface roughness and things like that. But there's a possibility that it might be a little bit better than what we got with Hubble.
Thank you.
Someone else would like to ask more?
So if not, perhaps we can close here. I think today we've really heard like fantastic talks, how our worlds will be transformational for the study of stars and galaxies and the cosmos. So really a big thank you to all the speakers of today. Thank you very much.
We'll reconvene tomorrow for the plenaries in the morning.
So a message from the LOC, actually 2 messages from the LOC. Tomorrow, if you are checking out of your hotel, check with your hotel to store your luggage there. We do not have storage space here at this facility, so please leave your luggage.
Thank you for a good tip.
The second thing is a reminder, we won't be back in the theater until tomorrow morning, but please, no food, no drink. The venue is really kind of mad at us right now because they keep cleaning up after us. Let's not make the venue people mad. So please, no food, no drink, tell your friends. Only in the theater, you can have it anywhere else, but only in the theater. No food, no drink.
And thanks, Jessica and all the dog for all your support. Thank you.
Like you get so many emails from you.
Oh my gosh, yeah. So like I really see you all are getting my emails in your feed.